Good afternoon to everybody. We're about to starting the session. Okay. We have the presentation, the International VLBI Service for Geodesy and Astronomy, with Harold Schuh from the IAG. Thank you, Harold.
Thank you very much, William, and ladies and gentlemen, again, welcome to my second presentation. And Alison, you said it's very difficult, very hard to give the last talk before the break, but it's even more difficult to give the first talk after the lunch break. So I try to be entertaining. And I'm going to give this talk on behalf of the IVS, the International VLBI Service, and its director of the coordinating center, Dirk Behrend, and Axel Nothnagel, who is the chair of the IVS. I was the chair of the IVS from 2007 to 2013. Just one slide how geodetic VLBI works. As you know, a network of antennas of telescopes is observing a quasar, and the time delay between the arrival time of a signal is measured, this time delay. And using the speed of light, the delay can be converted to a distance, and the distance is the component of this baseline vector toward the source. By observing many sources during 24 hours, for instance, we can determine all components of the baseline vector with a very high precision. That's the basic principle, and the role of VLBI is there's a lot of strong contribution. VLBI is the technique to determine, to measure the celestial reference frame, the CRF, which is important for astrometry, astrophysics. It also allows to determine all orientation parameters of the Earth in space and on the Earth, polar motion, UT1. This allows to do science with respect to Earth mass changes. The UT1 is very important. VLBI is the only technique that allows to measure UT1 minus UTC, which is needed for deep space tracking, to do solar system exploration, also needed for precise orbit determination, which is used and needed for a lot of GNSS applications and LEO applications. Concerning the terrestrial reference frame, VLBI is mainly providing the scale, and as you might know, very precise, stable, accurate terrestrial reference frame is needed, for instance, as a reference to determine sea level change, global sea level rise. What is the IVS? It's international collaboration of all organizations which operate or support very long baseline components. It was inaugurated just about 20 years ago in 1999. Currently, it consists of more than 80 permanent components supported by more than 40 institutions from more than 20 countries. And it is a recognized service of the IAG, also reports to IAU, the International Astronomical Union, and it is also a member of the WDS, the World Data System of the International Science Council. The goals of the IVS are to provide a service to support geodetic, geophysical, and astrometric research, and that's very important, to do the operational activities. Of course, also to promote research, development in the VLBI technique, and finally also to interact with the community of users of our VLBI products, integrate VLBI as a part of GGOS into a global Earth observing system. The main activities of the IVS are to provide the Earth orientation parameters, maintain ICRF, support maintenance of the ITRF, coordinate all VLBI observing programs for geodetic VLBI, set performance standards, establish conventions, issue recommendations for analysis software, set standards for analysis documentations, and also institute appropriate product delivery methods to ensure suitable product quality and timeliness. And that's the organizational structure of the IVS. We have the network stations, we have the correlators, we have data centers, analysis centers, We have the coordinating center operated at NASA Goddard Space Flight Center. We have a technology development centers and operation centers. IVS is carrying out a lot of training workshops and meetings. For instance, the technical operation workshop. This year we already had the 10th TOW to train the operators at the stations. A VLBI school has also been carried out already 3 times. The last one was this year in Gran Canaria to train and teach young researchers, PhD students and postdocs. We have a general meeting every 2 years. The next one is going to be in Annapolis, close to Washington, D.C., next year in March. This one was, by the way, in 2016 in Johannesburg, Hartbeespoort, with the elephants in the back. And we have meetings of special topics, topic groups like an analysis workshop, observation of near-field targets, etc. IVS publications, web presence, quite a lot. We have an IVS newsletter. Every 2 years we publish a biannual report. The general meeting proceedings also every 2 years, website mailing list. So it's very active to interact with and inform the community and also the other scientists interested in VLBI. That's the current situation of the network stations. Again, you can see a dominance of the northern hemisphere, mainly Europe and Asia. There are just a few stations in the southern hemisphere, mainly in Australia, 1 in Africa, 2 in South America, Fortaleza, and the Ago station close to La Plata. And O'Higgins is also very important on the Antarctic Peninsula. Yeah, now we come to the South American sites. Fortaleza, already mentioned it, operated by NASA together with the Brazilian hosts. And Ago La Plata, that's the 6-meter dish that was already used for almost 15 years in Concepcion in Chile, and then it was moved to Argentina. It's nice to have it and very important, but of course it would be even nicer to replace it by a modern, more modern standard telescope. That's the current observing program. We observe in 2 frequencies, S-band and X-band, and cover about 4 days per week. And there are additional so-called intensive sessions, short sessions, usually just between 2 stations, just to monitor UT1 minus UTC. These intensive sessions are carried out every day. Here is a table of the IVS products, Earth orientation parameters. From the 24-hour sessions, we determine all EOP. From the 1-hour intensive, we determine just UT1 minus UTC. There are also special sessions dedicated to monitor the terrestrial reference frame. And VLBI has its own terrestrial reference frame called VTRF. CRF, of course. And EOP already mentioned. And it is also possible to determine the tropospheric parameters and the baseline lengths, because baseline length is very precise from VLBI. There are corresponding observing programs. For instance, for the EOP, we have 2 rapid turnaround sessions per week with about 10 to 11 stations. The results are available no later than 2 weeks after each session. We have every 2 months, we have a TRF session with 12 to 14 stations, covering, if possible, all tectonic plates. There are also special sessions dedicated to monitor the celestial reference frame, in particular to observe the mostly southern sources on the southern sky, because as you can imagine, there are not so many sources that have been observed on the southern sky because of lack of stations. And there are also so-called R&D, research and development sessions, carried out once per month to investigate instrumental effects, study ways for improvement of the technique and of the products. And every 3 years, there has been a so-called CONT session to demonstrate the best possible results that can be achieved by VLBI, with 15 to 20 stations, observing continuously for 2 weeks. Now let me come to VGOS, the VLBI Global Observing System. Why did we decide and why do we need it? Of course, some of the systems are aging. Some of the antennas are getting older, 25, 30 years, even up to 40 years, have obsolete electronics. So this has to be changed, has to be replaced. And in parallel, there have been new technology developments. We have much faster and also cheaper antennas, digital electronics, high-speed network, automation. And on the other side, we have new requirements, as already demonstrated, for instance, in my first talk this morning and also by Richard. We want to get the 1 millimeter accuracy on a global scale to measure small effects like sea level rise and also processes related to earthquakes. So here we summarize again the goals of the new VGOS system: 1 millimeter position accuracy from a 24 hours observation. We want to carry out continuous measurement of station position and earth orientation parameters and get a turnaround time to get initial products within less than 24 hours. That's the first telescope. This is fully operational on the VGOS system. With the VGOS, it's a small, rather small, 12 to 13 meter dish. Some of the big antennas are as big as 100 meter. So imagine as big as a football field, and moving very slow. So they are very good for astrometry, astrophysics, but not for geodesy. But the small dishes, which slew very fast, 12 degrees per second, that's really fast. This allows to get more observations, covering a large bandwidth between 2 and 14 gigahertz, to avoid so-called radio frequency interferences, because nowadays everybody has a cell phone, smartphone in his pocket, causing a lot of trouble to VLBI with radio interference. And so we want to have a flexible frequency allocation. And also we want to sample the atmosphere much more frequently. So in the future, we will have 2 observations per minute. Currently, we have about 1 observation every 5 minutes. So we will increase the number of observables at least by a factor of 10, maybe even more. And that's the plan for mid-2020. We want to cover the full week, 7 days per week, continuous measurements with at least 16 station network. That is not just a dream. Fortunately, there have been several new radio telescopes which have been inaugurated in the last years. For instance, here, very far north, on Svalbard, Ny-Ålesund, close to the North Pole, even a twin telescope. Or another one, Ishioka in Japan. This one in Finland will be opened soon. It's almost operational now, and there will be the celebration. So it's nice working in VLBI. You can travel to all these places to the inauguration ceremony and have a nice party. And that's going to be the VGOS network by early 2020. Blue antennas which are already equipped with broadband. Broadband is an essential component of the new VGOS system. And red, VGOS antenna under construction or planned. So we hope Fortaleza will also be equipped with a new system. And here for Argo, we also hope to get a new system according to the VGOS specifications. And we did some simulations, and this might be interesting for you. What do we get from stations in South America? And what do we gain for X pole, Y pole, UT1? That's nutation X direction, nutation Y direction. And here you can see we simulated a 17 station network, and we removed Fortaleza. And this would decrease the quality of the results up to 15%, and that's quite a lot. That's quite a lot. If we add La Plata, we would gain a lot. In Y-pole, we would gain plus 13% improvement. And if we add another station, which we just in the simulation we put to Colombia, we would gain even more, plus 17%, plus 15%, plus 17%. That's a significant change of the quality of the results. Concerning data transport correlation, the legacy, the current network in S&X band currently produces about 2,000 terabytes per year. In the future, VGOS will produce 1,000 terabytes per day. So it's a very high demand with respect to data rate, communication rate, transport bandwidth, and storage capacity. In particular, the correlator needs to get access to at least 135 gigabit per second connection, which does not exist right now. But it's a plan, and we are optimistic to achieve it. Concerning the correlation, maybe you know there's this intermediate step which is needed to determine the correlation coefficient and to get the group delay. The correlation so far is being carried out at special, let's say, hardware, special computers, big computers. And the idea is to do software correlation on a cluster of PCs with off-the-shelf components. So the idea is to use 10,000 PCs during the night and doing the correlation. And here the challenge would be the power consumption of electricity for the processors and for the cooling. Just one small side remark. Just recently there was a project of the Event Horizon telescope which detected the first direct image of a black hole by VLBI. And this EHT and VGOS both are using exactly the same broadband VLBI technology, which has been developed at MIT Haystack Observatory. Of course, EHT operates in a much higher frequency domain, 230 gigahertz. VGOS operates around 10 gigahertz, but the signal chain backends, down converter, digitizer, recorders are exactly the same. So it was very nice to see that this spectacular result was obtained from using the same technology as we are using for geodetic VLBI. A final comparison between the current SX and the future VGOS system, which will, as I said, use rather compact telescopes, 12 to 13 meter diameter. Currently we have between 5 and 100 meter dishes. Very fast slewing rates, frequency range 2 to 14 gigahertz, and the recording rate up to 32 gigabit per second. E-transfer wherever possible. Ship disks only when required. For instance, from the O'Higgins station, there will probably be no broadband communication, so we still have to ship disks. And the complete signal processing chain is a digital one. Concerning the final products, we want to go similar to IGS to have different categories of the products, ultra rapid, rapid, and final products, and just look, for instance, on the expected accuracy for UT1 minus UTC. For the ultra rapid, it's 7 microseconds of time, and for the final product, it would be 1 microsecond of time. That's a factor of 15 better than the current situation. Currently, we are between 10 and 15 microseconds. So that's the goal. And finally, a funny picture. What can also happen, you can try your best, but you never know what can happen. And this happened at the station Yarragadee in Western Australia, that a kangaroo approached the telescope and pressed the emergency button, and everything was stopped. Maybe the kangaroo didn't like the telescope moving so fast. And so this happens sometimes, and it's nevertheless it's a funny picture. I like it very much, and with this I thank you for your attention. Thank you very much.
Thank you very much, Harold. Okay.
We were wondering about the data storage. Do you guys correlate the data and then throw away the raw data? Do you? Yes.
There's no other way. I was also asked by politicians, why do you throw away the raw data? And I told him, please give us a budget to build every day a big house like this, just to store the disks that we need to store the data. So it would be too much. So we have to erase the disks. Still, we are using disks to record the data, and after the correlation, the disks have to be erased and used again.
Is there another question or comment? Okay, I have one. Do you have some? Who are you talking with in Colombia about these ideas? Which institution?
Maybe Mike?
I don't know. The Geographic Institute could be? Okay. Maybe it was with the Geographic Institute.
Yeah.
Okay, thank you.
But this was just a simulation.
Yeah,
I could, if you like, I could put a station to any country. If you like.
Yeah, I understand.
Just tell me. For the simulation, it's easy.
Okay. Well, Harald, thank you very much. Okay. Please, yeah. And now the presentation is the International Laser Ranging Service, Michael Pearlman.
Okay, thank you. All right, I'm going to talk about the ILRS, International Laser Ranging Service. I'm going to start off, though, with a little bit of background on the satellite and lunar laser ranging, because I figured there may be some people in here that are not familiar with it. Once again, the person that helped put these together was Kerry Noll, but there were early contributions from a lot of other people. All right. Oh. Okay. All right. The laser ranging, the space technique, satellites equipped with retroreflectors, prisms, corner cubes. We're now tracking 100-plus satellites and the lunar reflectors with our network. The ground segment is a short pulse laser transmitter, pulse with 10 to 100 picoseconds. And fast detectors. These are avalanche photodiodes or microchannel plate detectors. We've got 40 sites that are tracking. Their performance, however, varies greatly. The observable is the two-way range measurement to the target. And once again, the characteristics are that it's a passive space segment, so it has an indefinite lifetime until the satellite re-enters. It's a simple range measurement. That is, there's no real processing in the sense of some of the other techniques. It's the only optical system in the space geodetic complex. Okay, all the others are radio techniques, so it's a little bit different, a little bit type of measurement. So philosophically, it's a very simple measurement. It's the range equals the two-way time of flight times the speed of sound divided by 2 with a correction for the atmosphere, a correction to extrapolate to the center of mass of the satellite, and also some calibration. In reality, though, it's a little more complicated. Geophysical models and the engineering models, of course, have to be working properly and can introduce bias issues. The state of the art is millimeter precision average measurements, and by average measurements, what I mean is we call them normal points, and just like the other techniques, rather than trying to take all of the data and stuff it through the machine, what we do is we form normal points. So they're averaged points, and they vary in time span from some number of seconds for very low orbiting satellites, and those spans increase as we go higher and higher. So we go up to GNSS, we go up to synchronous, then we're talking about collecting data for minutes for each of these normal points. We can track satellites from a few hundred kilometers out to GNSS. Some of the stations are tracking synchronous satellites, and of course some are tracking the moon. They track day and night, and as I said, some track the moon. Now these stations work independently, so each one will work on his own schedule. But a network of stations can be scheduled to work together if there's a particular campaign with some particular requirement in mind. Our targets are long-lived. Some targets have already been tracked for more than 50 years, in particular for studies of long-period perturbations. Now, I say these are long-lived. They, of course, don't compare with the VLBI folks who have targets that are much older, but in terms of targets that were launched from the Earth, this is 50 years is a long time. So the measurements are precision orbit determination and time series of station positions and velocities. Those are really the basic properties that come out of the laser ranging. The products are, of course, as has been mentioned, the terrestrial reference frame. The SLR provides center of mass of the Earth and scale, along with VLBI. I think on this version of the terrestrial reference frame, we're going to have a very pleasant surprise, we hope. For some time, the measurement of scale done by VLBI and the measurement of scale done by SLR has varied by about a part in 10 to the 9th. And, but with some, I say corrections of some operational issues that were found with the SLR, we're very hopeful that the two are going to be very, very close. And that would be very, very gratifying. I point out that we're very fortunate to have a geodetic product that's measured by two different systems. Because the closer that becomes, the more confident you are of the measurements that you're taking. The other things that we do is one of the big customers now for SLR is improving the understanding of the dynamics and modeling of GNSS orbits. The GNSS, the SLR is actually used on some of the GNSS satellites to compare with the radio measurements, and so that's a customer that is that we've had now for over the past 10 years or so that we never had before that. We also use it for calibration and validation of ocean and ice altimeter missions. As I mentioned before, we're also using it because of the long time span of the data on very stable satellites. We're looking at the static and time varying gravity field, and also looking at low order, low degree terms. And we're looking for long period perturbations that are important for the gravity field and the orbits. There are other things here, and you can read those. I just want to point out that the SLR is also used in space science, looking at satellite dynamics, some of the things, the satellite perturbations, and also relativity. Here's an example of some of the satellites we track. The ones on top are the geodetic satellites. They're spheres with retroreflectors all around them, so the orientation of the satellite isn't critical, so we know the extrapolation to the center of mass, which is critical to develop the products. Low Earth orbiting satellites, there are altimeters, there are gravity field missions, there are all kinds of applications that are supported by the SLR. And of course, in the higher altitude, we got the GNSS satellites. We have also the synchronous satellites to be included. I might point out there's one other application that's fairly new. It's a little far afield of what we do for the IAG, but some of the stations are now tracking space debris. Okay, they can actually track, some of them are satellites that have retroreflectors on them, And now some of the stations are tracking satellites without retroreflectors. And the data is of use in calculating the reentry, some of the reentry problems. So here's an example. So here's an example on the Topex as it was reentering, looking at the tumbling of the satellite. So another application, a little bit far afield at the moment. All right, the ILRS. We organize the ranging activities under the ILRS. So we do everything from predictions for data collection, from the rules of the game, et cetera, and the standards. And we provide the global ranging data and derived products to support research in geodesy, geophysics, lunar science, and fundamental physics. And of course, we spend a lot of the effort on the terrestrial reference frame, as I said before. It's one of the geodetic services of the IAG. It's a member of the GGOS observing system, and it provides the infrastructure necessary for monitoring a lot of the other, I call global change properties of the Earth. Everybody has to have an organization, and we're not an exception. Come on, Michael, they're not going to invite you back. Oops. Okay. We have a governing board like the other organizations, and we have a central bureau. The governing board determines policy, general policy of the ILRS. The central bureau actually runs the daily operations. So they under that they're the analysis centers, the data centers, the operations centers, and the network. And then on the other side, under the governing board, we have standing committees that provide expertise in a lot of the areas, whether it's analysis, or whether it's engineering for the network, or whether it's data formats. And we even have one for transponders, which are something that we're getting into. But they also spend time on precision time transfer. We hold workshops every couple of years to look at the science, look at the technology, look at what's on the horizon, look at major issues. The first one was in 1973, and we just had our 21st in December in Canberra. The next one is scheduled for 2020 in Kunming, China. And as I said, we have sessions on operations and technology, et cetera, et cetera. We have clinics for specialty issues to deal with these stations. I mentioned that. And here's a bunch of us in the 150 participants at the 21st workshop in Canberra. Now, you have to have something to do in the off years. So we have recently had technical or specialty workshops in the off years. And this is usually trying to focus on problems that the network might have, or particular areas where we think there's a lot of potential that hasn't been covered in the workshop. Okay, I'll have to give more of these presentations to get used to this. Okay, so this is the list of the specialty workshops. The last one we had was a couple of weeks ago in Stuttgart, and really focused on how to improve the economy performance of the ILRS network and its applications. And we have to recognize that SLR is a very expensive endeavor. It costs a lot of money to build these stations, and so we're looking at certain technologies that might might improve this situation. For the first time, we ran our first SLR school, providing tutorials on SLR and the ILRS. That was run the day before. The school had nothing else to do that Sunday, and so we had quite a large crowd that came in. In fact, we were oversubscribed, had to turn some people away. So obviously the school seems like a good idea, and we will continue it. The one comment we had is, can't we do it over 2 days rather than one? Too much material. We also have a special a Journal of Geodesy special issue on laser ranging. It's being put together. And we have, let's see, 18 papers so far that have been accepted, and there are another 4 that are in their review stage, and hopefully some of them will be added to it. So, and that is, I think, the first part of that, or at least part of that, is supposed to be out in the November time frame, which is now. So hopefully something will come very shortly. This is the network, and you've seen networks before here. These represent all the different stations, the ones that exist, the ones that are under discussion, and in different various levels of probability. So you see the ones in South America, 1, 2, 3, 4, the ones that have been mentioned already here. The San Juan and La Plata hopefully will be in operation very quickly, so all 4 of these will be operating. This is Arequipa. This is the station in Brasilia, which is doing a little bit better, but still has a lot to be desired, and we've had discussions with the Russians on that. I wouldn't put much confidence in these because they may be on the docket, but it's a long way off, so I wouldn't count on that. Some new stations in India that are coming up. Station in Java, the Russians want to put in. Station in Mexico. Station in Gran Canaria. Station in Yebus, the station in New Allison. They're a good addition to the network, but as I point out, we still have some very big gaps here. We had one in Saudi Arabia for a while, but that has operated for a number of years and then closed down. This is South America. You've seen that map already, I think, here. Showing the 4 SLR stations, the VLBI station, and DORIS, and the IGS stations. This is what's coming up. We got many new and upgraded stations coming online in the next few years. We mentioned La Plata, we mentioned San Juan, a new one in, actually a replacement in Metsahovi. NASA is undertaking new stations in Greenbelt, Haleakala, McDonald, and also in cooperation with the Norwegian Mapping Authority, building one for Ny-Ålesund. The Russian stations, Mexico, Indonesia, Spain, and Tahiti, the 2 in India that I've mentioned, Tsukuba in Japan, and Yebus in Spain. So there'll be a lot of new stations. However, they still do not fill the major gaps. Okay, and so there'll be a good enhancement to the network, but there'll still be some very big issues, geographical issues. Now, although we have all those stations, not all of them perform up to the level that we expect. This shows you the number of passes taken over the past year. The 3,500 passes we consider to be the minimum for a good operating station. Obviously, we've got some who deliver a lot more data than that, and we've got all these guys who really, there are many products that they don't have any impact on because they're not providing enough data. Some of these are being upgraded and hopefully will improve their performance. Some of them I'm afraid I don't have too much confidence in. In the analysis area, we're working on the development of the ITRF 2020 series. So that production is moving along. We have replaced a number of models, in particular the center of mass model for some of the geodynamic satellites, and that's where we think the improvement is going to come in the scale. There are some improvements in how we're handling the data. The next step is we'll be implementing some models for low degree, low water gravity field, actually extracting them from the data. And we have a new LARAS geodetic satellite that we'll be adding to the mix so that it'll have an effect on the terrestrial reference frame. So here are the issues and the challenges. Many geographic gaps, primarily in Latin America, Africa, and Oceania, that we've got to work on that, and it's the same with the other techniques. We have a mix of new and old technologies. Since the stations don't have to work together, okay, we've got some very new stations and some very old stations, and some of the stations are upgrading, some of them are not. Interestingly enough, the best performing station, the station at Yargadee, is probably the oldest technology. Okay, so you got a lot of stations, brand new stuff, good operating stuff, but the station at Yargadee is still. Oops. So we do suffer from the lack of standardization in system hardware, and also in some of the operations because of the hardware. We have some data quality issues in the SLR, and I've just mentioned the correction or the improvement in the models for the extrapolation to the satellite center of mass, and we think that's going to be a dramatic improvement. The number of targets we have continues to grow. We're up over 100, and we're getting applications all the time for new satellites, which means we're going to have to be a little bit hard-nosed about this. Just not enough capacity. That's it.
Thank you very much, Michael.
Questions?
Yeah?
Dave.
Thanks, Mike. One question, and I probably should have mentioned it during the co-location presentation, but if there are representatives here from either Brasilia or San Juan SLR stations, I would be very interested in discussing some co-location efforts with you in regard to GNSS.
Hey, that's an offer. Don't pass that up.
So this is Dave Stowers from JPL.
Mike, could you say a few words about lunar laser ranging?
Yes. And don't tell them that I didn't mention too much about it. It'll come down on me. Okay. The lunar laser ranging is in a funny situation. We have a number of stations that range, once in a while. We had Apache Point that was doing very, very well. And the Apache Point situation is a little bit uncertain right now. We don't know what's going to happen, mainly because the guy who was running it isn't sure what he's going to do. So that's unfortunate. But there are a number of new stations. There are stations in China, stations in Russia, that are coming online. So we do expect there to be more coverage. And we'd also expect that there will be new retroreflectors on the surface of the moon very shortly. I know that Doug Curry is working on his idea is one large cube, which should be very interesting. So I think it's being rejuvenated. I think it's going to take time. One of the problems with us was that it was neither fish nor fowl.
So my name is Frank Lemoine.
Frankie, you here? Yeah. One of the problems that we had was that lunar ranging really wasn't accepted by the people who were funding things as a satellite, for satellite laser ranging. And the lunar guys were interested in putting their money elsewhere. So this thing has really suffered by being in the middle. But I was hoping that with the 50th anniversary of the Apollo 11 landing, there'd be some enthusiasm, and maybe that's the case. So we haven't forgotten about the lunar guys. Anybody else? Okay. Well, thank you very much.
Thank you very much, Michael. Okay, now we have a presentation that has been recorded from Mr. Frank Lemoine. He is at the Greenbelt NASA Observatory, and he belongs to the directing board of the International DORIS Service. The conference is the International DORIS Service.
So my name is Frank Lemoine. I'm chair of the So my name is Frank Lemoine. I'm chair of the International DORIS Service. Meeting of GGOS days is that, and the reason you are watching a recorded presentation at this meeting of GGOS days is that none of the members who are authors of this paper could travel to Rio de Janeiro to make this presentation. So we are recording this presentation with the assistance of the video services at the NASA Goddard Space Flight Center. The purpose of this presentation that I'm making is to present you an update on the DORIS system and the International DORIS Service, and I intend to present to you some new information and clarifications on some points regarding the DORIS system. So I'm going to present to you first an update on the DORIS system. So just to remind you what DORIS is, DORIS, the acronym stands for, in English, Doppler Orbitography and Radio Positioning Integrated by Satellite. And these are the translations courtesy of Monsieur Google in Spanish and Portuguese, so I hope they're correct. DORIS is a French civil tracking system designed for precise orbit determination. It's for high accuracy ground positioning of beacons and for high accuracy orbit determination of low Earth orbiting satellites. The present performance is 6 to 9 millimeters RMS radio orbit accuracy as measured by independent high elevation satellite laser ranging data. It's an uplink and centralized system based on measurement of Doppler shifts of RF signals transmitted by a worldwide network of beacons. It was developed by the French Space Agency and in partnership with the French Survey and Mapping Agency, IGN, and the Space Geodesy Research Institute, the GGOS. So the system is composed of a network of stations around the globe. The satellite receivers can receive up to seven stations simultaneously. This is the DGXX receiver. And it consists of a control system that receives the DORIS measurements from each satellite every orbit. There are two frequencies, 2.036 gigahertz and 401.25 megahertz. It's a dual frequency system, which of course allows for correcting the ionosphere delay. The precision is 0.3 millimeters per second, and that's based on an ultra-stable oscillator that has a stability in terms of Allen deviation, delta F over F, of a few parts in 10 to the minus 13. The signal is free, and there is no limitation on the number of satellites that can carry DORIS receivers. So on the left, you see the current DORIS dual frequency instrument, the DGXS package, which is carried on the current satellites that are in orbit. It includes a redundancy of the ultra-stable oscillators and a diode near real-time orbit determination system, basically a very advanced Kalman filter that can produce 3.5 centimeter RMS radial orbit accuracy in real time. The provider is Thales Systems. The system has an excellent availability on the JSON-2 mission, which has just ended. After 11 years, the DORIS system was continuously available. The JSON-2 mission ended because of problems with the solar array and the spacecraft gyros, not because of any of the tracking systems, including DORIS. So there are 3 types of beacons in the DORIS network. The first is the standard beacon, which is known as an orbitography beacon. The second class of beacon is called a time beacon, and these are beacons that are connected to atomic clocks, and their purpose is to transfer the TAI up to the DORIS spacecraft. And then there's a master beacon, which also relays information. I'd like to clarify some of the nomenclature regarding what a DORIS station is, because sometimes I think there's a little bit of confusion. So a DORIS station consists of all the equipment at a DORIS site. That includes the transmission and management units, the ultra-stable oscillator on the ground, the backup supply system, the antenna, and accessories, and sometimes a weather station. The DORIS beacon is actually the unit which produces the transmitted signal. It includes the ultra-stable oscillator, and it generates the DORIS signal, which is sent via the cables up to the DORIS antenna. The DORIS antenna transmits the DORIS signals. That's depicted here on the left. And it's the precise orbit determination that determines the coordinates of the reference point of the antenna, while taking into account the antenna phase variations, which are determined from measurements in an anechoic chamber. This is a bit of an eye chart, but it lists the DORIS-equipped satellites that have flown or are flying. There are 14 missions that have contributed to the International DORIS Service since 1990. 8 missions are now decommissioned or over, and there are 6 DORIS satellites currently in orbit. The orbits include polar orbits, generally sun-synchronous, and then the TOPEX-adjacent orbits around 66 degrees inclination. And the altitude range is between 700 and 1336 kilometers. The mission with the most longevity is the Spot 2 mission, which was launched in 1990, and it continued in operation until 2009. Of course, I'm biased, but I think the most important missions are the missions that are dedicated to the measurement of global mean sea level, and those are TOPEX Poseidon, JSON-1, JSON-2, and now JSON-3. So this gives you sort of a visual summary of the time span of the different missions. In sort of magenta are the missions that have flown. So these include the Spot satellites, Envisat, JSONs 1 and 2. The current missions that are on orbit, that includes Cryosat-2, HY-2A, Soral, Sentinel-3A, and Sentinel-3B. And then future missions that will launch in the near future and into the 2020s. So in the near future, we have the launch of the Chinese satellite HY-2C, which will carry a DORIS receiver. And next year in November, approximately a year from now, we will have the continuation of the JSON-3 mission, which is the Sentinel-6 JSON-CS satellite. This gives you a depiction of the geographical distribution of the DORIS network. There are approximately, as I said, 60 beacons around the world. The distribution is homogeneous between both hemispheres, and the DORIS team at the CNES and at the IGN have worked very hard to achieve this distribution. but it's also due to the cooperation and dedication of the many host agencies that have contributed to the system over the years. So the DORIS system is managed by a single entity. It has a long, typical stations have a very long time series, on the order of 21 years on average. The network availability hovers around 90%. And that's because at any given time there will be a few stations that are out of service. And because of the remote locations, it can take time to service stations that have minor problems. Half of the stations are located on islands or in coastal areas, and there's a good north-south distribution. 48 of 59 stations are co-located with other techniques. That includes GNSS, satellite laser ranging, and VLBI. I'd also point out that there are 28 stations that are co-located with tide gauges relatively close by. Now I'd like to review the three types of monumentation that we have in the DORIS network. And for more detailed information, I can refer you to this paper by Jérôme Saunier, which was published in Advances in Space Research in 2016. So the Type 1 monument is a tower placed on a load-bearing pillar of a building. This particular choice provides good sky clearance visibility and access to power when other options are not available. The Type 2 monument is a stainless steel tripod installed on a 1.5 meter high concrete pillar, and the concrete pillar is always appropriately anchored into the ground, into bedrock, for example, if it's there, with steel rebars, or into soil 1 to 2.5 meters with a deep foundation. And this is an example of an installation on Ascension Island. The Type 3 is a rigid steel tower installed on a concrete block that's compliant with stability requirements for pillars. This monument gives you a slightly higher ground clearance than Type 2, and it's used to provide sufficient sky clearance at a particular site. In the lower right-hand side of the figure, you can see a depiction of how that ground monument looks like underground. So the concrete pillar extends 1 to 1.5 meters into the soil, and then there's a concrete slab foundation that's also present. And we believe this is a very stable type of monument. So if you would like more information on this monumentation, there's a document on the DORIS website authored by Jérôme Saunier that describes this in detail. So I'd like to discuss now some of the improvements that are underway in the DORIS system. The first improvement that's been underway now for several years is the implementation and installation of the Type C Starrick antennas. The Type C Starrick antenna controls the location of the 2 gigahertz phase center to 1 millimeter. The early generations of that antenna only controlled the location of the phase center to several millimeters. The deployment of these Type C antennas started in 2014. There are about 18 stations currently equipped, and probably on the order of 10 to 12 will have a time series of 2 to 2.5 years that will be sufficient for being included in ITRF 2020. The second implementation that's underway is the 4th generation beacon, and it has updated electronic components. The most important attribute is that it allows the DORIS antenna to be up to 50 meters away from the DORIS beacon or electronic equipment. And the whole purpose of this is to allow a better viewing environment for the DORIS antenna. One of the stringent requirements that the DORIS team works very hard to achieve is to have sky visibility down to 8 degrees elevation and as few encumbrances or disturbances in the field of view to avoid disturbances in the DORIS signal. So I'd like to comment on the positive impact of the GGOS project. There are many countries that have responded to the call to build the core network infrastructure, and as a result of this, DORIS has moved to the Wetzel Observatory in Germany, which is now a 4-technique site. DORIS was installed in San Juan in 2018, and the DORIS site at Ny-Ålesund was renovated in 2018. There are also plans to install DORIS, of course, at the Tahiti Geodetic Observatory at the site called Papanu, and that will be in cooperation with NASA, and that will occur sometime in the 2020s. There is a synergy between the different techniques, and there have been detailed studies between the DORIS and VLBI teams to see how the two techniques can cohabit together. And as a result of these GGOS efforts, the DORIS team has put together a ground antenna characterization of the error to develop an error budget that was published by Jérôme Saunier, and a detailed assessment of the stability of the DORIS network documentation. So this slide lists the DORIS stations in the southern part of the Western Hemisphere. The site with the longest time history and longest occupation is Rio Grande, installed in December 1987 in southern Argentina, followed by Arequipa and Cachoeira, Arequipa in Peru and Cachoeira in Brazil. Arequipa, of course, is a site that has co-located with satellite laser ranging. So this chart shows the visibility circles at 800 kilometers altitude. So it's how the different satellites can see the DORIS signal. And there's good coverage over South America and into the Eastern Pacific and the Western Atlantic. We are working with colleagues in Chile to update the DORIS station on Easter Island. So to summarize, the DORIS system has been operational since 1990. In February 2020, we will celebrate the 30th anniversary of the DORIS system, of the first measurement on Spot 2. There are 59 ground stations. The 4G beacon is being deployed, and the new satellites will include JASON-CS, Sentinel-6A, as I mentioned previously, the joint NASA-CNES mission SWAT, and the HY-2C and 2D missions scheduled for launch in the near future. So I'd like to give you a brief summary now of the IDS products. So first of all, we produce SINEX files, series of station coordinate solutions of Earth orientation and station coordinates. This is updated quarterly. These are weekly solutions. We provide reference frame solutions, which are position and velocity solutions. That's a cumulative solution that's developed over the entire time series up until the recent time, and that's developed bi-yearly. We have solutions for Geocenter. There's actually a pilot project that's underway to provide refined estimates of Geocenter, and the CNES Associate Analysis Center produces precise orbits which are distributed on a routine basis. So there's a rich source of information for DORIS at the DORIS website that includes presentations, reports, technical information, and extensive bibliography. If you're interested in the different technical aspects of the DORIS system, you can sign up for different electronic mailing lists. There's a YouTube channel, but the YouTube channel has information on the different attitude laws of the DORIS system, and there's detailed information on the characteristics of the different satellites that make up the system. We also have an annual activity report, which you can subscribe to or you can view on the web. And if you're interested, we encourage you to subscribe to our DORIS newsletter, which is published several times a year. So to summarize, the International DORIS Service has been a service of the International Association of Geodesy since 2003. We have 6 active analysis centers, 4 associate analysis centers, and that includes DGFI TUM, Technical University of Munich, which was just approved as an AAC about a month ago. We have 2 data centers, the NASA CDDIS and IGN. We have a combination center, an analysis working group, and different working groups working on different topics. So the current activities include the data processing for ITRF 2020. We're also looking at the near real-time delivery of DORIS Rhinex and diode orbits that will start with JSON-3 in early 2020. You should contact Denise Detmering at DGFI TUM or Pascal Ferrage at the CNES for more information. There will be a call for proposals for an IDS station sometime in early 2020. What is an IDS station? It's a station that's dedicated for scientific purposes, and there have been a few of these over the years, but we are looking to initiate a call for proposals early in 2020. We are planning for an IDS school, which will discuss the DORIS technique and DORIS products. Planning is underway, so you should look for updates again early next year. And we have several working groups that you might be interested in joining. Alexandre Coer of the CNES is working on a pilot project for determination of geocenter from DORIS data, and you should contact him for more information. We're also working to make precise orbit determination software available with documentation so new analysis centers can join the IDS more easily. As many are aware, it shouldn't be a prerequisite for someone to write their own orbit determination program in order to join IDS. And finally, we have meetings next year that includes the analysis working group meeting, which will be in the spring, and the IDS workshop, which will be held in the fall 2020. That will be in Venice, Italy, associated with the annual meeting of the Ocean Surface Topography Science Team meeting. So, muy obrigado, muchas gracias. Thank you for your attention. I hope you have a productive meeting at GGOS Days. And if for further information about DORIS and IDS, please contact the IDS Central Bureau, the Director of the Central Bureau, Laurent Soudarin, Jérôme Saunier, the Network Manager, or myself as IGS Chair. Thank you for your attention.
Zulia in Venezuela, and he is also the president of the SIRGAS Working Group I, related to the reference system and to the reference frame of SIRGAS. The presentation is Operation of the SIRGAS-CON network, a look at the performance of SIRGAS Working Group I during the 2015-2019 period.
Oh, thank you, William. Good afternoon again. On behalf of Sonia and Mauricio, I'm going to talk a little bit about the activities in our working group. And just for the sake of simplicity, I'm going to switch to Spanish. Before that, the slides are in English. If you see grammar outlier, please tell me for update the presentation and then distribute it to you. Okay. El grupo de trabajo, iba a cambiar al inglés, al español. El grupo de trabajo 1 de SIRGAS es uno de los que ha estado activo durante los 26 años de existencia de SIRGAS, creado en 1993 junto con la iniciativa del proyecto SIRGAS. Y desde ese entonces el objetivo principal que se ha perseguido es establecer en Latinoamérica, establecer en nuestra región, un marco de referencia altamente consistente que materializara, ¿no?, al sistema de referencia terrestre internacional. Desde ese entonces, desde el 93, los primeros logros se cristalizaron, se evidenciaron en 1995 con la campaña SIRGAS 95 y luego en el año 2000 con la campaña SIRGAS 2000, esas dos grandes campañas que permitieron la materialización de las primeras o los primeros marcos continentales acá en Sudamérica. Sudamérica y luego en América completa. Las personas que estuvieron a cargo de ese trabajo inicial comenzando con Melvin allá en Venezuela. Si Claudio estuviera aquí diría que eso fue una dictadura, ¿no? Desde 1993 a 2004. Saludos a Melvin y Claudio si nos están viendo online. Luego el mismo Claudio, luego Sonia, luego Virginia, y hasta la fecha nos ha correspondido estar al frente del grupo de trabajo. Siempre teniendo como principal objetivo o como línea estratégica proporcionar a la región una densificación del ITRF que sea accesible a todo el usuario, no solamente en el área de la geodesia, sino de la geociencia en general. Pero además, otra línea estratégica ha sido garantizar el mejoramiento continuo del marco de referencia. Y en función de eso ha habido una evolución bastante significativa de la red, entendiendo el marco de referencia como una red de alta precisión. Desde la red del 95, que solamente cubría Sudamérica, hasta la red del 2000, hemos visto cambios no solo en la distribución y la cantidad de estaciones, sino en el modo de ocupación, desde redes pasivas hasta la red continua que tenemos hoy en día. Pero también hemos visto cambios en el tipo de observación como tal. Antes solo GPS y luego ahora tenemos GNSS, GPS GLONASS, inicialmente es la que estamos procesando. Pero nuestras estaciones ya rastrean otro tipo de constelación, Beidou y Galileo. O sea que en un futuro próximo quizás estaremos también incluyendo ese tipo de observables en nuestra estimación. Y también se ha visto a lo largo de todo este tiempo una amplia variedad de aplicaciones que se le están dando a la red, no solo para el marco de referencia geodésico, sino también para temas que tienen que ver con la geodinámica, con la geofísica, la ciencia de la atmósfera y aplicaciones en la agrimensura y en la topografía, el catastro, etc. Eso ha obligado a ir reorganizando el grupo de trabajo para ir adaptando la realidad que tenemos desde el punto de vista de nuestra configuración actual de la red hacia el logro de esos objetivos primarios o esos objetivos estratégicos a los que hacía referencia. En función de esto, entonces, a la fecha, el grupo de trabajo tiene como responsabilidades principales mantener el marco de referencia, y esto lo hacemos a través de SIRGAS-CON, de la red SIRGAS de operación continua. Es un trabajo, William lo decía en su intervención de esta mañana, es un trabajo de hormiga que a veces no se ve, pero que muchas personas estamos trabajando en eso para garantizar a la región un marco de referencia altamente confiable. Además, otra responsabilidad que es muy importante tiene que ver con el desarrollo de capacidades, la transferencia de conocimiento, principalmente hacia los centros de procesamiento que se instalan en cada país, y se asume que esos centros de procesamiento luego divulgan esa información, divulgan ese conocimiento, valga la redundancia, para hacer que el marco de referencia tenga sea la principal alternativa al momento de satisfacer aplicaciones en el ámbito de la geomática, de la geodesia, de las geociencias en general. Es decir, garantizar un aprovechamiento máximo, óptimo del marco de referencia que se está proporcionando a través de SIRGAS. Ok, Virginia esta mañana comentaba la composición del grupo de trabajo. Simplemente destacamos que a la fecha 9 centros de procesamiento están a cargo del mantenimiento del marco, con 2 centros de combinación. Uno funciona acá en el IBG, que es el centro de combinación primario. Bien. Sobre la red, actualmente la red está compuesta por 411 estaciones, decía GNSS, capacidad de rastreo multiconstelación. Sin embargo, a la fecha solo estamos considerando en nuestros cálculos observaciones GPS GLONASS, y los datos de esas 411 estaciones son proporcionados por una gran cantidad de agencias gubernamentales, académicas, de investigación, que de forma voluntaria ceden los datos para que nosotros dentro de SIRGAS podamos hacer el procesamiento y podamos hacer hacer el cálculo para la generación de productos primarios. Productos primarios que inicialmente se trata de soluciones semilibres de la red, soluciones luego que son ajustadas al ITRF y eventualmente soluciones multianuales con las que es posible luego evaluar la estabilidad a largo plazo del marco de referencia. Bien, ahora, esos datos son proporcionados bajo ciertas políticas, acuerdos entre las instituciones y SIRGAS, siempre respetando la voluntad propia de cada institución. Sin embargo, hay que decirlo que muchas de las instituciones que aportan los datos los ofrecen de forma libre. Y hemos hablado esta mañana, se ha comentado esta mañana sobre la importancia que tiene compartir los datos de forma libre, ¿no? O sea, especialmente en esto del GGRF, del GGOS y ese tipo de lineamientos que están viniendo y que nos hacen reflexionar acerca de la política de datos. La red que se procesa a intervalos semanales se suele subdividir por mera simplicidad también. En este caso, una red continental está bajo la responsabilidad del Centro de Análisis asociado al IGS para SIRGAS, que opera en el DGFI allá en Alemania, y luego las densificaciones nacionales son asignadas a cada centro local. En total, 9 centros. Uno que responde directamente ante el IGS, por decirlo de alguna manera, y los 9 centros que funcionan en diferentes países de la región. De acuerdo a esta ilustración, vemos los países en donde funciona cada centro. Ok. Acá. Ahora, si nos preguntan, ¿qué características tiene la red SIRGAS-CON? O sea, pregunta de examen, ¿qué características tiene la red SIRGAS-CON? La principal, el crecimiento constante. Hemos visto en los últimos años, los últimos 4 años solamente, 94 nuevas estaciones que se han incorporado a la red. Y esto nos dice mucho, ¿no? En primer lugar, el gran interés que tienen diversas instituciones, diversos países en seguir aportando a SIRGAS. Pero también hay que decirlo, del 100% de las estaciones que están en nuestra red, estamos ofreciendo soluciones aproximadamente de un 90%. El otro 10% que no es mera casualidad, están concentradas en Centroamérica y la parte norte de Sudamérica, no están aportando datos por N diversidad de razones que no vienen al caso en este momento. Esta cantidad de estaciones que vemos se ha venido incrementando en función del tiempo, obliga a ir haciendo redistribuciones para que cada centro de procesamiento pueda manejarse de manera efectiva, y eso es fundamental porque seguimos un cronograma de trabajo bastante estricto, ¿no? Luego de la observación que hace cada estación, hay cierto tiempo para calcular y luego cierto tiempo para generar la solución. Sobre esto se comentó algo esta mañana, los 3 eventos, digamos, que nos han obligado a hacer redistribuciones recientes: el cese de funciones en Costa Rica, el cese de funciones en la Universidad del Zulia, allá de donde yo soy, y el nuevo centro de procesamiento que afortunadamente se ha instalado en Chile y que de una u otra manera nos ha permitido darle salida a este problema de la distribución y la capacidad que tiene cada centro de procesamiento de trabajar, ¿no? Como bien. Entonces, sobre el procesamiento, sobre la operación continua de las estaciones, hay unas preguntas que debemos hacernos, ¿no? Lo ideal es que todas nuestras estaciones, las 411 estaciones que tengamos o que tenemos, funcionen de esta manera. Una medición continua, con un procesamiento continuo que de una u otra manera nos permita generar productos que satisfagan los objetivos de SIRGAS, ¿no? Sin embargo, tenemos estaciones que no cumplen ese criterio. Entonces, algunas preguntas que debemos respondernos. ¿Todas esas estaciones realmente están siendo utilizadas en los países para las actividades o para las aplicaciones para las que se establecieron y se incorporaron a SIRGAS-CON? ¿Cuántas estaciones realmente necesitamos si queremos hablar de marco de referencia? Tomando en cuenta que en los últimos 4 años se han incorporado casi 100 estaciones. Ahora, de toda esa cantidad de estaciones y la potencial inclusión de más estaciones, ¿nuestros centros de procesamiento realmente tienen esa capacidad técnica y logística para seguir asumiendo más estaciones? ¿Nos hacen falta más centros de procesamiento? ¿Cómo atacamos ese problema? Luego, ¿las estaciones que tenemos realmente cumplen los criterios de calidad que nos están emitiendo, nos están emanando en términos del GGRF? Aquello de la disponibilidad de los datos, la calidad per se de los datos, el acceso libre a los datos, etcétera, etcétera, etcétera. Por supuesto, estas son preguntas que, producto de reflexiones en estos últimos 4 años, y que tocará al nuevo grupo de trabajo 1 ir respondiendo en la medida de lo posible. Sin embargo, desde 1996, cuando se instala el primer centro de procesamiento SIRGAS en el DGFI, hasta la fecha, la red sigue manteniendo una alta calidad a largo plazo y una alta consistencia, una consistencia homogénea, y lo más importante, todo dentro del ITRF. Ese procesamiento SIRGAS-CON, que tiene que ser obligatoriamente a intervalos semanales, y me atrevería a decir, no tenemos la capacidad todavía a intervalos diarios, ¿no? Pero es estrictamente necesario en América Latina porque vivimos en un continente que se mueve, o sea, cambia, ¿no? subducción por un lado, deformación hidrológica por el otro, carga atmosférica por allá arriba, etcétera, etcétera. Eso solamente es posible por un trabajo colaborativo entre diferentes instituciones, entre diferentes recursos humanos que de una u otra manera interactuamos para poder ofrecer un marco de referencia a todo el continente, para poder garantizar compatibilidad en el tratamiento y adquisición y tratamiento de información geoespacial, para contribuir con una implementación efectiva del GGRF en Latinoamérica y para definir una infraestructura observacional que permita estudiar cierto tipo de fenómenos asociados al sistema Tierra, cambio global. El punto de partida para poder cumplir estos 4 puntos, elementos, es la solución semanal y la solución multianual que se genera a partir del trabajo continuo de los centros de procesamiento. En los últimos 3 años, 2015 a 2018, vemos entonces que la red mantiene sus niveles de calidad en el orden de más o menos 1 milímetro en posición horizontal, más o menos 3 milímetros en la vertical, y vemos que es algo que se mantiene. En el caso de este año que estamos reportando, 2018-2019, las soluciones individuales de cada centro de procesamiento, luego de que son analizadas, luego de que son evaluadas, demuestran alta consistencia entre ellas, consistencia a nivel interna, consistencia a nivel externa. Y por supuesto, si están bien las soluciones individuales, la solución combinada también debería estar bien, ¿no? Por lógica. Entonces, es lo que estamos viendo acá. Por ejemplo, el RMS medio de la solución individual de cada uno de los centros de procesamiento luego de que es alineada al marco de referencia. Es meramente algo ilustrativo. Y vemos que es un nivel de calidad bastante alto, de acuerdo a la distribución de estaciones que se tiene para cada centro de procesamiento. Para obtener estas soluciones altamente precisas, no es usar un software, no es tener datos de alta calidad, no. O sea, es tener un buen grupo, un buen equipo de trabajo que sepa hacer las cosas, ¿no? Y ahí el grupo de trabajo históricamente se ha enfocado en, repito la idea, desarrollar las capacidades técnicas en cada institución que decide albergar un centro de procesamiento. En estos 4 años y en este último que estamos reportando también, el desarrollo o el desenvolvimiento de los centros de procesamiento ha sido muy exitoso y es algo que se debe a trabajo en equipo. O sea, uno dice, no, yo soy presidente, no, pero es que no soy el presidente del grupo, es que somos un grupo con diversidad de opiniones y hemos sabido encontrar dentro de nuestra diversidad una forma, la mejor forma posible de hacer las cosas, ¿no? Y aquí estamos viendo un ejemplo de eso. Y tenemos 2 centros de combinación que también demuestran un rendimiento bastante bueno. Ambos centros de combinación generan las soluciones definitivas de la red SIRGAS-CON y ambos resultados, es decir, o ambas soluciones que genera cada centro de procesamiento son plenamente consistentes, son prácticamente idénticas, ¿no? Por decirlo de alguna manera. Y es lo que se ilustra aquí semana tras semana. Vemos algunas diferencias de un centro con respecto a otro, que, bueno, si analizamos bien al detalle, están asociadas con situaciones a las que no somos ajenos, ¿no? Por ejemplo, en una solución se considera una altura de antena que no era, o un centro de procesamiento dejó de incluir una que otra estación, cosas que son rutinarias, que no deberían suceder, pero que suceden, y que, bueno, repito, no somos ajenos a cometer ese tipo de errores. Semana tras semana, entonces, en este último año, 2018-2019, nuestra consistencia interna, es decir, la solución que se compara con la semana anterior de la misma red SIRGAS-CON, mantiene los mismos niveles de calidad a los que hacemos referencia anteriormente, pero también cuando comparamos semana tras semana nuestra solución individual con respecto a la solución del IGS, vemos que se mantiene, o sea, volvemos otra vez, hay consistencia. Y entonces, en función de esto, podemos seguir afirmando que a la fecha, la red SIRGAS-CON, nuestro marco de referencia que densifica el ITRF en América Latina, sigue teniendo más o menos 1 milímetro en la horizontal, 3 milímetros en la vertical. Un logro de un trabajo en equipo que se hace de manera organizada. Y Virginia lo comentaba esta mañana, creo que William también lo comentó en la mañana en su intervención, lo que tiene que ver con el entrenamiento y la importancia del desarrollo de capacidades, la transferencia de conocimiento. Eso para efectos de las actividades propias del grupo de trabajo 1 es fundamental, por el dinamismo dentro del grupo de trabajo. Este año o este periodo se han registrado 2 cursos de capacitación, uno en la Universidad de Santiago de Chile, y eso permitió la instalación de un centro experimental en esa universidad que hace poco, septiembre de este año, se consolida como centro oficial, y un curso de actualización en el Instituto Geográfico Militar del Ecuador, en Quito. Eso se dictó en agosto de este año. Pero también ha sido prioritario, en la medida de lo posible, darle cabida a SIRGAS, y en especial a los productos que se derivan de SIRGAS-CON, en cualquier foro, cualquier evento, cualquier medio que nos permita lanzar a SIRGAS al mundo, ¿no? No solamente reunirnos una vez al año, ¿no?, entre nosotros mismos, sino también darle darle más cabida, más salida a nuestro trabajo cotidiano. Todas las presentaciones que se han hecho dentro del ámbito del grupo de trabajo están disponibles en la página web. Aquí solamente hago mención a los más recientes, un artículo que se publicó en la revista Coordinates, eso fue en 2017, si mal no recuerdo, y un póster que se presentó en la asamblea de la IUGG en Montreal, ahora en 2019, febrero fue eso, sí, febrero. La IUGG, en julio. Ok, la intención es que vayan a la página web y vean todas las publicaciones que están ahí, porque si no, no ven la página, ¿no? Entonces después Laura, no. Sí, por favor. Por favor. Entonces, bueno, a partir de estos 4 años de aprendizaje, 4 años de trabajo en equipo, 4 años donde hemos visto que ese trabajo en equipo da resultados muy buenos, algunos comentarios finales que quizás nos puedan servir de reflexión. Entonces, en primer lugar, estamos conscientes del rol que juega la geodesia hoy en día, la geodesia moderna, no solo para Latinoamérica, sino para todo el mundo. Y ese rol de la geodesia moderna exige un marco de referencia altamente preciso. En la región, en Latinoamérica, es SIRGAS ese marco de referencia que nos da vínculo directo al ITRF. SIRGAS-CON no solamente es una densificación de este marco, sino que también es una infraestructura observacional que brinda soporte a una amplia variedad de aplicaciones en las geociencias. De hecho, desde que comenzó el simposio, hemos venido conociendo y discutiendo aplicaciones que de una u otra manera se sustentan en las estaciones SIRGAS-CON, cuyas coordenadas se calculan gracias a la labor cotidiana de los centros de procesamiento. El grupo de trabajo 1 sigue asegurando que la red mantenga sus niveles de calidad, ya los mencionábamos, y entonces generalizando 1 milímetro en horizontal, aquí me faltó una I, y 3 milímetros en la vertical. La colaboración y el trabajo en equipo son clave fundamental para poder mantenernos en este nivel de operatividad. Y aquí entonces tenemos que agradecer a todas esas instituciones y a todas esas personas que están involucradas en SIRGAS y que sobre todo pueden garantizar que sigamos todos dentro de SIRGAS, ¿no? En lo personal, agradezco estos 4 años de esta confianza que han depositado en nosotros, y bueno, los logros son compartidos y las cosas malas las asumo yo solo, ¿no? Como presidente del grupo de trabajo. Ok, todos entonces a seguir trabajando dentro de SIRGAS. Y entonces, como estamos hablando de reflexiones, 2 preguntas que quedan al aire, ¿no?, para la discusión. ¿Qué nos falta por hacer dentro del grupo de trabajo 1? ¿Y hacia dónde debe ir el grupo de trabajo 1 en esta nueva gestión que comienza a partir de este año 2019? Entonces, bueno, este ha sido un breve resumen de nuestro desempeño, de nuestras actividades durante este periodo, y cualquier información adicional, con mucho gusto, ahora o en el receso o cuando regresemos a nuestras casas por correo, etcétera, etcétera. Por su atención, muito obrigado, es lo único que sé en portugués, y bom dia, ¿no? Bom dia, ¿no? Okay, thank you very much for your attention.
Thank you very much, Victor. Questions?
Por un reconocimiento, me gustaría que quienes están presentes de los centros de procesamiento se pararan para que la gente los conozca. ¿Puede ser? Chile, Costa Rica, USACH, IBG, Uruguay, GNA, por favor.
IGAC.
IGAC. Uruguay. INEGI allá. Bueno, gracias porque son los motores de todo esto, ¿eh?
No more questions?
Un comentario a tu pregunta si se necesitan 400 estaciones o más. En otra lámina tú dijiste se necesitan las soluciones semanales porque hay mucha deformación en América Latina. Y eso es verdad, pero por la misma razón se necesitan más estaciones.
Sí.
Japón es mucho más pequeña que América Latina, es más pequeña que solo Brasil.
Sí.
Y ellos tienen 1200. Entonces, yo creo
Sí.
se necesitan no menos, sino más estaciones.
Más estaciones, exacto. Y hacia allá va la reflexión, ¿no? Podemos tener muchas más estaciones, pero nos hacen falta más centros de procesamiento. Y ojalá podamos cumplir esa meta, ¿no? De que en cada país de la región tengamos un centro de procesamiento. Eso creo que sería ideal. Y así sí, las estaciones que vengan, ¿no? Buenísimo, o sea, las que quieran venir, que vengan, bienvenidas todas. Entonces, bueno, es un tema, claro, de discusión, sí, estamos de acuerdo, sí. Una invitación también, ¿no? Así, subliminal, ¿no?
Thank you, Victor. We are on time. In this schedule, we have 10 minutes for discussion, but those 10 minutes finished 2 minutes ago, so it's over. Thank you very much for your attention.
Som, 1, 2. Som.
Good afternoon. Welcome to the last session of our joint session of GGOS Days and SIRGAS Symposium 2019. I would like to introduce you Thomas Gruber, the speaker of the next presentation, the International Gravity Field Service and its components. Thomas Gruber is senior scientist at the Institute for Astronomical and Physical Geodesy at the Technical University of Munich, co-director of the GGOS Bureau of Products and Standards, member of the GGOS Science Panel, and member of the advisory body of the International Gravity Field Service. Thomas, thank you.
Thank you, Roberto. I didn't know that I have so many tasks. This talk is theoretically given by Riccardo Barzaghi, the director of the International Gravity Field Service, but he was not able to come here, and he was asking me if I could take over this task, and I'm happy to do so. So what I would like to do now is to introduce a little bit a few more details about the IGFS. Many things were already mentioned today during the day, so I will not stress too much on details, but at least that you get a nice overview. Actually, I just made a deal with Roberto. I stay 5 minutes here to get more 5 minutes in the next talk. So I will be quick here. The IGFS is the umbrella of the various services related to gravity field. You will see in a minute which services these are. So the IGFS itself is not a real service in that sense, so it doesn't provide data, but all the sub-services or the sub-elements of these IGFS are delivering something. And that is important to understand, so that this is a coordinating activity, and they have also what's called bureau, I think, no, it's on the next slide, just forget the central bureau, which is then responsible for coordinating these activities, and specifically which is responsible also to define metadata for all these different gravity field related products. The Central Bureau is managed by the Aristotle University in Thessaloniki in Greece, and these are all the services which have been mentioned already today. And I come back anyhow to this. I don't want to go into detail right now. Just to give you a quick overview. This is about the Central Bureau and the tasks, and I will do it very quickly because they have a lot of very detailed things about these metadata stuff, which I will not go here or present in detail about that, but it's an important task that I would like to mention. So the tasks is done by all these people here mentioned on the slide, and what they do is that they make this IGFS application as a web application for creating metadata, so either for G means gravity or for N means geoid, and they also have in addition another tool which I'm not fully aware about, to be honest, which is called metadata locator, which I think is a search tool in order to identify where you can get specific data. This is the IGFS website, so if you go there you will have a link to these metadata, which are the blue boxes here in the bottom. So this is what they do here. They define online applications for creating metadata for gravity and for geoid, as I mentioned, and also then for searching specific data sets. This is very important, very helpful. It's I think it's not yet fully operational, but you can have a look on the website and you can at least try it. In future, it's important to understand what is the basis or what is the fundament and what are the standards which are applied for specific data sets. As soon as you combine these data with something else, you have to be aware about what is the basis for this data. And this is an attempt to describe the data in a very good way, in my view. So now there are many slides about details about the web application and things like that, which I would not go into detail here because that's too yeah, to very specific stuff about the implementation of the computer stuff. So I will go very quickly forward. It's under development, as I said. It's not yet fully operational, but it's already in a very good stage. So in principle, this is on the beta version, as they call it. So in principle, it's accessible. You can try it and at least have a look how it looks like. So let's go further. And this is, for example, just giving you an idea. What is the category? What are the categories which are implemented in this metadata? So these are reference information, identification. So in principle, yeah, who provided that, to get in touch maybe in case of questions about the distribution, about standards and conventions which are used here, about data and quality, and so on. So this is what is defined as metadata in the case here for all these gravity products. Okay, that's what IGFS and GGOS. You had here one slide which shows a little bit how IGFS people contributed to GGOS meetings. For example, this was here, that IGFS also participates in activities of Laura's group about the unified height systems inside the GGOS consortium. And also in the definition of the essential geodetic variables for gravity, which is also an important task where I am also involved in some sense. There were two meetings which were co-organized by IGFS so far, which were basically inside the series of the Commission 2 gravity meetings. So one was no, this was not, sorry, I mismatched. But these are the meetings where the gravity people more or less meet every 2 years. And these are very efficient meetings, so those who work on gravity, I really recommend to go to these meetings to try to participate, because there you meet all the people working on gravity, geoid modeling and things like that. And it's usually very helpful, and you get direct in touch with all those who compute models and things like that. There's a plan for the next one next year, just to announce it already at this point. I think the date is not yet fixed, but it's probably in September in Austin, Texas, organized by Srinivas Bedatpur. These are the topics which are usually addressed in these sessions, so all what is related to gravity in that sense. So it's from observations to final models and applications in terms of, for example, mass transport. Then the IGFS also has one, still running, I'm not sure if it's finished, a project which is heavily supported by IGFS, which is about the Mediterranean geoid determination. So modeling of the Mediterranean geoid, which is the picture shown here. So they also work a little bit in scientific applications in some sense. So let's move to the services itself. So the different services which are under the umbrella of IGFS. So there is the BGI, the Bureau Gravimétrique International, which is maintained or driven by the group from Observatoire Midi-Pyrénées, I think it's a French word, in France, where they collect, in principle, all gravity measurements. This is a tricky task, collecting gravity measurements. As you might know, because gravity observations you don't get easily, they at least get something. And according to their maps, it's not such bad. But the problem is they may not give many of the point data to the community, because it is restricted. So partially one can get at least maps or something like that in form of a digital map, but I mean a colorful map, but not a data map. It's a bit difficult situation in my view. They do their best, what they can. So the coverage is very good, but don't think that you can get all this data which are read here. That's not possible. So gravity, in contrast to many other data, is still restricted, and that's the pity of this whole business, and where we have a lot of problems
really to improve, for example, also global models. There is also some kind of collaboration between the BGI and the other service about geodynamics and earth tides, which I will address later a little bit, but this is about absolute and superconducting relative gravimetry data, which are also designed for observing time variability of gravity, for example. There is here some statements which are about where to place or how to use, or which stations should be equipped, for example, with these high performance gravimeters, which is mentioned here, for example, that there should be some kind of core stations, reference stations, also related to the height reference system, which is then addressed in the next talk, I guess, by Laura anyhow. So this is an important quantity to be observed on fundamental or reference stations, I would say. Yeah, here are the maps which I was just talking a little bit about. So there are a number of stations around the world, but as usual distributed more towards the north than to the south. But these are also quite expensive measurement systems and need to be maintained a lot. And there is also the one in La Plata, which should be known better by the BKG people than I know it. Yeah, about the global models, this is my favorite service because I'm using that a lot, and I recommend to everybody to use it. It's really well established. It's their service for the global models. It's the only one. And there you can get a lot of nice things, and you specifically also not only just the data but also educational material. I use it a lot for lectures, even in projects for the students, where they can do some nice computations, visualizations and everything. So it's really very nice implemented and by GFC in Potsdam. There's the GeoID service, also was mentioned before, which collects and distributes, if possible, again, not every GeoID is just available, regional GeoID solutions. This is maintained by Polimi, the Politecnico di Milano in Italy. So there, for example, they provide different GeoIDs. Here there is the example for the South American GeoID, which is also included in this service, so you can get it from there, I guess, with references and so on, and some visualization. Here are, for example, all the GeoIDs which are in the system of the GeoID service from South America, here from this area. Even merging national GeoID are done. For example, in Europe, they made an attempt to merge these GeoID solutions here from Spain, France, Italy, Switzerland, Portugal, I think, and Greece. I guess this was in the frame of the GeoMed project. And they also found then there are slopes, tilted surfaces, systematic differences in these GeoIDs which are not reasonable, so they applied some detrending and get then a more reasonable view. So you see, it's not such an easy task to combine different things, and for this you need definitely to know all the background knowledge which was used for computing these GeoIDs. So this again brings me back to these metadata. Yeah, then they organize schools and training courses from time to time, basically in order to educate students on how to compute regional GeoIDs. Then it's about the IG, so the Geodynamics and Earth Tide service here, which I already mentioned somehow. So this maintains these database for the superconducting gravimeters and the time variations of these gravity accelerations. This is maintained, I think, by BKG, correct? Yeah. These are the products, basically what I just mentioned more or less, all the data and corrections. This is the map, the related map, which is used, or which shows the data stations for the superconducting gravimeters. So again, and additionally absolute gravimeters, which are shown here. And just to complete here, there is another service which is about the digital elevation models. I should be careful because this service is driven by Curtin University in Australia and Esri. Esri is a company, as you know, a big company working on that. And what I definitely note, like, it's a personal statement right now, it's not from Ricardo, that when you try to get their data set, you end up always at Esri to use their software, which I'm not able to use because I don't have no clue, I never used it. So, and that is not the point. I would see that a service should work like this. This is, again, to repeat, it's a personal statement, yeah. So therefore I stop with the items here to talk more. And there was already mentioned also the new service about combination of the time variable gravity, which is in principle an attempt to make it more user-friendly for selecting the right time series of gravity models from GRACE, for example. Okay, I think I should stop here because I'm not sure if I spent my 20 or 15 minutes now.
Thank you, Thomas. Any questions?
So I do not fully agree with your statement that IGFS does not have its own product, because the cost G is, as it written here, is the product center of the International Gravity Field Service. So it's not like the other services. It's like the product center of the ILRS. It's a product for time variable gravity field. So I think there is a clear distinction.
No.
Yeah,
I don't agree, because this is, you get a time series of gravity models, so if you put it there or here, it doesn't matter. And cost G is not inside IGFS, it's also below IGFS.
No.
If the picture in the beginning, I should, maybe from a theoretical point you are right, but from a practical point I would say not.
No. We completely disagree. Maybe Hermann can also comment it.
Yeah, but what you see here,
yeah.
What is the difference if it goes from here to that or to that box? I don't see. It's the only difference is the circle or ellipsoid, and this is a square.
We should not discuss it because it's quite clear. The executive committee of the IAG decided the coast is a product center of the IGFS, and the next product center will be the height reference frame.
Okay. May I make one comment to this general stuff in GGOS? So because now you start discussing, we can discuss about that. You see these kind of charts in all these presentations today. And if you know how the history was, these charts are expanding and expanding. It's always getting more and more boxes. I personally have no overview anymore about this, all these boxes, to be honest. And what you do in geometry is not correct to be done in gravimetry.
Just another fact. It's not true that these boxes are increasing, they are decreasing. We had 14 services, now we have only 12.
Let's save some discussion for the dinner.
After a few
Thank you, Thomas. Again, please. Next presentation by Dr. Laura Sánchez, the International Height Reference System, or with a little modification, advances in the realization of International Height Reference System.
Yeah, this one, yeah. It's okay.
Oh, it's okay?
Yeah. Okay, so this afternoon I will present you a summary about the activities we are facing for the establishment of the International Height Reference System. Here is a very long list of co-authors, and this is because The activities I will present here are a joint effort of many entities within the International Association of Geodesy. You can see here working groups, study groups, subcommissions, commissions of the IEG, the International Gravity Field Service, and the two GGOS bureaus, the one for networks and observations and the other one for products and standards. And with this slide, I just want to point out that the realization of the International High Reference System cannot be done by one person or one institution or one country. It's a big challenge, and it can be realized only within an organization like the International Association of Geodesy. So, which is the usual way to determine heights? You know, we perform leveling, we determine or we observe these level differences. The level differences between two neighboring points are multiplied by the mean value of the gravity value between these 2 points, and we add these differences multiplied by gravity. What we are doing here is determining potential differences. If the initial point of our leveling is located on the geoid, we call this the physical height, and I say physical height to talk generally and need particularly in orthometric heights or normal heights, just physical heights. So, what we do with leveling is to measure the potential difference between one point, decided as the geoid, and another point. And this is the potential difference between these 2 points, and we use gravity value to express these potential units in meters, and we get the height, the physical heights of the point of our interest. This is what we have today, and if we try to determine the geoid using gravity values with heights defined in this way or in this system, we get what we call a local geoid, and local means that it's the equipotential surface passing through the reference point we use for our vertical networks, so a local geoid. What is the objective of the International High Reference System? We want also to determine potential differences, you can see here, between the points located on the Earth's surface and a global equipotential surface. The gravity field of the Earth had many, really an infinite number of equipotential surface, and with this definition, we are saying which of all the infinite number of equipotential surface we are selecting as reference for the determination of these potential differences. This is a convention, so we select this arbitrarily. It is known, it is fixed, and it doesn't change. So with this is not a problem. Our problem is to determine the potential values on the Earth's surface in order to estimate the potential differences with respect to this global reference surface. The realization of this reference surface in a global frame is now possible thanks to the satellite gravimetry, in particular chain grace and GGOS. Really, I wanted to say GGOS, grace and GGOS. Because with these 2 satellite missions, we can realize this reference level with a very high precision in a resolution of 100 meters about. And we just have to take care on improving the resolution not provided by those missions. Okay, so the International High Reference Systems wants to determine these potential differences with respect to a global unified reference surface, and the potential values should be localized or the position of these potential values should be given in the ITRF, and the determination of potential values and ITRF positions should consider their variations with time. And another characteristic of this definition is that we should use meter and second as units. So we have to use meter and no inches or feet on this kind of units. What we need to realize this system? We need physics points where we can say, this is a point referring to the International High Reference System, and we need the coordinates of these physical points. So the first need here is the establishment of a reference network, and we decided to follow the same example like the ITRF. So we should define a global core network, and this network should be extended by means of regional and national densifications. And furthermore, the global network should be collocated with the so-called geodetic observatories like AGO, for the combination with the ITRF, the gravity absolute or gravity laboratories, and also the determination of the reference time. It should be realized by continuously operating stations in order to detect the formations of the reference frame. It should be collocated with reference state gauges and national vertical networks to support the integration of the existing high systems to the global one. And it should be collocated with reference stations of the new gravity reference frame. A main requirement for these reference points is the availability of terrestrial gravity data to better determine the potential values. So we start station selection in the GGOS dates 2016, and at the beginning we get the support of Mike Pearlman with his Bureau of Network and Observations. We have some interchange with the Bureau Gravimétrique International, and we also got in contact with the regional experts in reference frames and gravity field modeling in order to define a core network. I call this core network because this is our start point to see how easy or how complicated it is to realize this system in real life, I'd say. This doesn't mean that the station selection is closed, or that we cannot accept new stations, or these stations will be working forever. That this is only a start point. It's a living network, and it should be extended by regional and national densifications. This is all what I want to say regarding the reference network. And now I would like to talk about the determination of the coordinates. So, according to the definition, the International High Reference System is a combination of a geometric component given by the ITRF coordinates and a physical component given by the determination of potential values at these ITRF coordinates. Today, we heard the presentations of the different IAG services providing the geometric products, and the determination of these coordinates follows the ILRS conventions, and we are not taking care about this. We want to realize at first the determination of the potential values, and then see how can we interact with these conventions. For the moment, we are taking these as they are. According to the GGOS terms of reference, the expected accuracy for the vertical positions is about 3 millimeters in the position, and about 0.3 millimeters per year in the velocities. Our goal now, our target is 1 centimeter, so we are working 10 times worse as the GGOS requirements. And we should also determine the variations of the coordinates with time, but for the moment we are trying to determine static coordinates only. There are different methods for the determination of the potential values, but I just want to mention two. And one is the use of the global gravity models of high degree. I hope most of you know this equation. We have the global gravity models are given with these coefficients, and the easy way of life will be take the ITRF coordinates, put them in this equation, and get a potential value, and this is a dream. According to a previous study of Rommel, he says that if we use these models for the determination of physical heights, we can get accuracies about 4 to 6 centimeters in well-surveyed regions. That means North America, Europe, Australia. And in sparsely surveyed regions, the expected accuracy is about 20 to 40 centimeters, and in some cases 1 meter. So if you are living in Europe and you need a physical height with 4 centimeters accuracy, and you are happy with this accuracy, fantastic, you can use this approach. If you are in, I don't know, in Colombia, and you need a physical geodesy with an accuracy of 50 centimeters, this is perfect for you. If you need some higher accuracy, we have to improve these models. And if you are in Colombia and you want to have an accuracy of 4 centimeters, then you should provide your terrestrial gravity data to the International Gravity Field Service in order the people who are computing these models can work with your data. The only way to improve these models in your regions is including terrestrial gravity data in the determination of these models. At the moment, there are two promising proposals. One is the combination of global gravity models with gravity effects from global topography, and I think the next presentation of Thomas is in this direction. And the other one is the computation of the new Earth Global Gravity Model 2020. The other possibility is the determination of this potential following the same methods used for the determination of the geoid. Also, the combination of a satellite component plus a residual component provided by terrestrial gravity and the potential generated by the terrain effects. As I mentioned, the availability of these three data is LR, GRACE, and GGOS. We can get a resolution of 100 kilometers, a very, very good precision. But the mean omission error globally is about 45 centimeters. So what we have to do is to reduce these 45 centimeters to 1 centimeter. So now we have some conditions that before were not possible, and this is the availability of this data. So the idea is to apply the same methods we use for the geoid determination to estimate the potential values, and there are two general possibilities. One is the Molodensky approach, which allows us to determine the potential values on the Earth's surface, and the other approach is the Stokes approach, which allows us to determine the potential values on the Earth's surface. The problem is the modeling of this potential requires a different series of approximation, and this generates different, and this makes that different methodologies produce different potential values. In order to compare different methods of computation, we started in July 2017 what we call the Colorado experiment. And the idea here was to take terrestrial gravity data, airborne gravity data, the same digital topography model, and some GPS leveling data, and try to compute geoid, quasi-geoid, and potential values for this region and for this control line. This is a test profile with 250 points or something like that. And to use this data and try to compute these three things using a set of basic standards, and then to see what we get. We performed three computations. So one computation, it was discussed in I think in Copenhagen, 2017. The second computation was discussed in April this year in Vienna, and the third computation was discussed during the IUGG General Assembly in Montreal. Here, very quickly, the different groups contributing to these experiments. In total were provided 15 solutions. And here, I don't want to go into the details, but just a list of the different methods they use for the computation of the potential values, geoid and quasi-geoid. And what we do is the following. So this test profile, this is the topographic profile, and heights are going up to 3,200 meters, more or less. And our colleagues have to compute potential values. Then we convert these potential values to geopotential numbers, and then we convert the potential differences in normal heights in order to compare the different results in meters. And you see here, these are 40 solutions. One solution we have to reject it because it was total out of this range. And here you can see this solution present a mean discrepancy with respect to the other one of about 16 centimeters, and we suspect that this outlier has to be with the handling of the different constants in the global gravity model and in the reference ellipsoid, and Detlef talked about this morning. If we remove this outlier, we get here another outlier with the mean discrepancy. And if we remove this one, we'd get here 12 solutions for 15 solutions. And you can see that the mean value are very, very similar. So the largest outlier is this minus 1.4. And this similarity in the mean value for all these comparisons is the use of a global gravity model based in SLR data, GRACE, and GGOS. So this is really an achievement of these global gravity models. On the contrary, the range of the differences are very large. So we have differences up to 13 centimeters. And if you compare these values with the topography, it's clear that we have to improve the modeling of the topography effects in these computations. So what we learn here, the 12 solutions of 15 agree quite well in terms of the standard deviation with respect to the mean value. These comparisons reflect only discrepancies between computation methods, so we assume that the input data are free of error, and we have to think about a proper error propagation analysis. We want to compare these results with the leveling results along this test profile. The discrepancies are high correlated with the topography, and one source of this is the handling from the terrain gravity effects, and the other one is the conversion from geoid to quasi-geoid for the determination of the potential values. So here there is a degradation of the precision. The larger difficulties reported by the colleagues contributing to the experiments is the handling of the air gravity data, and also the handling of the different constants in the global gravity model and the reference ellipsoid. And someone used GRS80, other ones used the WGS84. And the question was if we need a new reference ellipsoid that replaces these two to avoid these discrepancies. For the future, we are trying to generate a document with the tile standards for determination of potential values. It should provide guidance for the regional and national densifications of the international high reference frame. For the next 4 years, we are establishing now study groups and working groups to evaluate how to improve the modeling of topography effects, the determination of the potential change with time, and how to determine a really accuracy of the estimations. We are working in the determination of the potential values of the network, shown in the third or fourth slide. And we are trying to explore to install an element for the heights within the International Gravity Field Service in order to make this procedure a routine. I think that's all. Thank you.
Thank you, Laura. We have time for a quick question. No. Laura, how about the distribution of stations, the even distribution of station? What is the expected effect of this preliminary distribution?
So in the station selection, we try to get an homogeneous distribution worldwide. If you see, the geometric reference networks are very, very dense here, and here is less. So we try to get a more or less homogeneous distribution. Of course, there are many stations in the region that so colleagues want to include their stations here, but we say, wait. We try to solve this core network, and then you can decide how many IHRF stations you can have in your region or in your country.
Yeah, thank you. We can move to the next presentation. Thank you, Laura, again. Professor Dr. Silvio Freitas, President of the Group 3 of SIRGAS project, will talk about the past, present, and future of our vertical group.
Good afternoon. I'm going to speak in Portuguese. Some students asked because the presentation is transmitted. Then, I'm sorry, I changed for Portuguese. A razão dessa apresentação, agradeço a inserção no programa dessa apresentação, porque é uma oportunidade de mostrar um pouco, talvez algumas conquistas, mas as dificuldades presentes que nós temos relacionadas com o sistema de referência vertical para os SIRGAS. Eu distribuí mais ou menos a sequência, fazendo uma sequência passado, presente e perspectivas futuras. Mais ou menos alguma coisa que eu conversei com a doutora Laura Sánchez, ela concordou comigo que era uma boa visão para ser apresentada. O que acontece? O SIRGAS teve, na sua primeira campanha, em 1995, ele teve um grande sucesso no estabelecimento de uma rede tridimensional única para a América do Sul. E uma questão que surgiu mais ou menos ao mesmo tempo, o que fazer com as redes verticais no continente? Então, não tínhamos significado físico para as altitudes, não existia uma homogeneização e conexão para um contexto internacional, e cada país tinha o seu datum vertical, distintos datum verticais, cada um estabelecido numa época por períodos diferentes também. Como que foi encarado no contexto do SIRGAS? Então, em primeiro lugar, foi estabelecido, por exemplo, Durante a Assembleia Geral da IAG, no Rio de Janeiro, em 1997, foi criado o grupo de trabalho 3, chamado Datum Vertical, à época. E as ideias iniciais era que deviam ser diagnosticadas as características de cada uma das redes verticais dos países membros, aquela época ainda mais ou menos centrado na América do Sul, e em termos do que seriam, como seriam as redes, as características de cada um dos data verticais, qual o estado atual destas redes, os dados disponíveis e que ações seriam necessárias para fazer a modernização dessas redes dentro de um contexto para a unificação. Então, o que nós chamamos de sistema vertical de referência do SIRGAS, em inglês SIRGAS Vertical Reference System invertido, então foi bastante discutido, vamos dizer, durante uma reunião que teve do Grupo de Trabalho 3, que aconteceu no Chile, durante um evento na área de geodésia que aconteceu no Chile. Então, como deveriam ser encarados os problemas de cada rede nacional, os data verticais, dentro de uma perspectiva de unificação dos sistemas. E a integração das redes verticais no sistema, também fazendo a sua conexão com a rede tridimensional, vamos dizer, a rede SIRGAS já existente. Bom, no ano 2000, foi a campanha do ano 2000, a campanha SIRGAS, GPS SIRGAS, do ano 2000, incluiu já estações, uma perspectiva de estações que podiam, que estariam nas divisas nacionais, e também os marégrafos, incluindo estações GPS próximas aos marégrafos. Bom, às vezes estou colocando uma referência e essas referências estão apontadas no final da apresentação. E grande parte delas está disponível na página do SIRGAS. Bom, o que foi considerado fundamental dentro do Grupo de Trabalho 3? Como que foram adquiridas as perspectivas mais fundamentais do Grupo de Trabalho 3? Foi graças a um evento que aconteceu na Colômbia, Vertical Reference System, que aconteceu na Colômbia, foi em 2001. E mais ou menos as diretrizes de ação foram estabelecidas lá. Então, nesse trabalho, que também tem uma publicação, o IAG Series, um volume do IAG Series dedicado a esse tema, e que foi coordenado pelo professor Dreves aqui presente. Ele foi, vamos dizer, organizador, um dos organizadores, também o Luiz Paulo, acredito que foi organizador desse volume, e mais uma pessoa, recorda quem, Luiz Paulo? Bom, mas de toda forma tem a referência no fim. E alguns trabalhos foram também inseridos dentro dessa apresentação, que contém já uma perspectiva do que à época se visava para a unificação das redes verticais. E para entender um aspecto bastante importante, foi a conclusão que devíamos utilizar como altitude física as altitudes normais e também os números geopotenciais. Quer dizer, essas diretrizes já foram estabelecidas à época e também vinculadas às estações SIRGAS, vamos dizer, já em IHRF. Bom, alguma coisa começou a acontecer de diferente, vamos dizer, no contexto global. O que aconteceu dentro de um contexto global? Em 2003, apareceu o GGOS. Então, foi um acontecimento. E um dos temas que surgiram depois, dentro do desenvolvimento do GGOS, como um tema central, número 1, foi a unificação de sistemas verticais. Porque não era um problema só nosso aqui no contexto SIRGAS, era um problema global. E era um problema bastante importante. Enquanto, geometricamente, existiam soluções muito consistentes em nível global com relação ao espaço do geopotencial, essas soluções não existiam. Então, tem um trabalho muito importante que ele consta, que tem uma análise bastante importante da nossa... um de nossos ícones das redes verticais, a doutora Laura Sánchez, aqui presente, em que ela fez um trabalho a gente chama em português trabalho de formiguinha, de juntar informações, e tem um relatório muito importante de uma análise das redes verticais na América do Sul. Também uma outra formiguinha aqui presente, nós temos o Roberto Teixeira Luz, que fez a sua tese de doutorado, ele fez praticamente um manual de modernização de redes verticais. É um trabalho extremamente importante no sentido de como agir para modernizar e com uma particularidade, considerando sempre todas as nossas restrições que nós temos nos países latinos, muito afetados por problemas econômicos, distribuição de bases de dados, etc. E aí, então uma quantidade foi estabelecida, uma quantidade de ações foi estabelecida. O que aconteceu mais ou menos como consequência? Essas figuras estão disponíveis também na parte do SIRGAS, mostravam, por exemplo, aparentemente, redes clássicas, mas um país tem 2 data verticais. Tem outro que tem 6. 6 data verticais. Como que a gente faz como é que a gente encara isso? E a distribuição destas redes, nós temos praticamente um país que tem uma rede homogênea dentro do nosso contexto. Os demais foram mais ou menos desenvolvendo suas redes de acordo com a sua necessidade e de acordo com suas possibilidades. E temos grandes espaços vazios. Então, esse é um aspecto bastante presente na nossa realidade. Bom, o que foi diagnosticado assim num contexto mais geral? Não existia, não existia uma forma única de fazer os níveis de referência. Muitos deles são a partir de marégrafos, porém, nós temos países que são landlocked, não têm acesso ao mar, e eles têm o seu datum vertical. Então, e como unificar essas redes? As redes foram baseadas no nivelamento geométrico, em métodos de nivelamento geométrico. Porém, em geral, não tinham gravimetria associada. Em geral, eram aplicadas somente correções teóricas. Então, maior parte das redes já estavam sem essa informação, vamos dizer, gravimétrica associada, somente do ponto de vista teórico. Então, os data verticais apresentavam discrepância entre eles. E aí vemos figura que já foi apresentada hoje, mas eu acho muito importante, né? Mostrando toda a estrutura geodésica que é disponível, os serviços, vamos dizer, os pilares da geodésia, os produtos e como isso chega ao povo. E daqui que saem os recursos para manter tudo isso aqui. Então, eu acho que é muito importante essa visão aí. Bom, então aí entra numa história bastante conhecida, que já foi discorrido no dia de hoje, né? Então, foram projetos a partir do GGOS, da concepção do GGOS, né? Por isso que estou me atrevendo a colocar GGOS Ihde, né? Então, a resolução da IAG, que finalmente definiu, né, um potencial de referência, e como que o SIRGAS adotou isso aqui. Então, o SIRGAS ele participa dessa, vamos dizer, desse grupo de trabalho conjunto, né, que a Laura é a chair desse conjunto. Aí tem um trabalho que a gente apresentou no contexto da revista cartográfica, as estratégias para modernizar, e também já referidos à base de publicações aí que existe. Bom, e aí estabelecemos, então, uma sequência, vamos dizer, os protocolos do grupo de trabalho 3. Isso foi a partir de 2015 que nós estabelecemos isso. Isso daí foi divulgado a primeira vez em um workshop que aconteceu, vamos dizer, em Quito. Bom, então, desde 2011, que os problemas associados, quer dizer, foi concluído, né, para unificação, por ajustamento de números geopotenciais. Então, aquela heterogeneidade existente de conhecimento, principalmente dos institutos nacionais, foi sempre uma barreira para se trabalhar. E como organizar essas bases de dados? Então, foi adotada uma estratégia já desde 2012, então, workshop, escola juntos. Então, foram realizados 6 eventos desde então para formar as pessoas. Então, isso daí envolveu mais de 200 pessoas e elas, como fundamental, nós contamos com dois conjuntos de aplicativos, 2 pacotes de aplicativos, um desenvolvido pelo professor Dreves e a Laura Sánchez e outro desenvolvido pelo Roberto, que foram aplicados nessas escolas. Os presentes focos, aqui eu destaco que, mais ou menos, que são os assuntos tratados nas escolas, a busca que nós estamos agora vendo de como introduzir as variações temporais. Aqui, a distribuição inicial de estações, como já foi abordado, tanto pela Virgínia quanto no global, dizendo que essas atividades estão no contexto do Grupo de Trabalho 3 também estão sendo coordenadas pela doutora Laura Sánchez, né? E o que se conseguiu? Ela conseguiu mobilizar as autoridades nacionais, fazer estudo e planificação de novas estações de acordos com quer dizer, o Working Group que ela coordena, que faltou, Joint Working Group. E algumas estações já foram decomissionadas, foram replanejadas e tem uma figura mais recente, né, em que se apresenta isso. E atividades em cursos tentando entender a relação entre os data verticais dos países e o novo referencial global proposto. Então, aqui, as estações que foram decomissionadas e novas 2 estações que surgiram. Então, essa aqui é uma outra apresentação daquela lâmina que a Laura apresentou na sua palestra. Aqui, mais ou menos, também a Laura já apresentou esses tópicos. Aqui, simplesmente, como é que nós integramos informações vindas, vamos dizer, da modelagem do geopotencial e o que vem do nivelamento. Então, essa aqui é uma fórmula de integração. E o nosso ponto-chave, está destacado na sequência, é a determinação do potencial perturbador no ponto na superfície. Então, é isso que a gente busca a solução. E, feito isso, a gente consegue determinar a discrepância entre o datum local, datum vertical local, e o datum global. E, como finalização, existem muitas coisas a serem realizadas. Todavia, o que a gente manifesta aqui nós necessitamos um maior protagonismo dos institutos nacionais, em termos dessa contribuição. Somente três países completaram essas tarefas até agora. Argentina, Brasil e Uruguai, que completaram essas tarefas de ajustar suas redes em termos de números geopotenciais. Essas esperanças introduzidas pelo ILRS e o IHRF são assim, extremamente positivas. Agora, temos que ver como promover essa transição de um sistema vertical local, sem significado físico, para um sistema global com significado físico. Então, os novos conceitos, considerando datum vertical, redes baseadas em números geopotenciais e modelagem do campo da gravidade, são importantes, porque uma, do ponto de vista da rede, a realização da rede, a realização do referencial, também tem que se pensar nas aplicações. Por exemplo, isso tem que integrar com o referencial global e tem que propiciar aplicações práticas. Por exemplo, como recuperar o valor do geopotencial em pontos na superfície, ou como obter uma altitude com significado físico com suficiente precisão, partindo do posicionamento GNSS. Então, são os dois aspectos. Então, mais ou menos, são essas ideias. Aí, só avançar um mais para mostrar que as referências estão lá. E é importante que talvez a gente tenha uma discussão com um maior tempo durante a reunião do grupo de trabalho, que vai acontecer na quinta-feira, nessa sala que é no andar acima. E, assim, dessa forma, lá pretendemos discutir mais ou menos o futuro desse grupo de trabalho, mesmo que tenha a perspectiva de mudança da estrutura, vamos dizer, do SIRGAS, principalmente em relação ao grupo de trabalho 3. Assim é que eu agradeço muito a atenção. Muitas graças, thank you, e essa seria a minha apresentação.
Thank you very much, Professor Silvio. We have time for one quick question. Anybody? I have a comment or ask you. From time to time, people raise the question about the normal heights or orthometric heights. Do you have some comment about this?
Bom, altitudes ortométricas, elas são, existem somente do ponto de vista estritamente teórico, porque necessitamos de um valor de gravidade média ao qual nós não conhecemos e fazemos aproximações. E na altitude normal nós não fazemos aproximações. Então, essa mais ou menos é uma visão que... E as duas, nenhuma das duas, os pontos em uma lagoa, nenhuma tem os pontos numa lagoa, nenhum tem a mesma altitude normal, nenhum tem a mesma altitude ortométrica. Então, o problema persiste para as duas.
This is because SIRGAS recommended the geopotential numbers.
Sim. Todos os pontos da lagoa têm o mesmo número geopotencial. Por isso que são coordenadas primárias.
Yes. Thank you again, Professor Silvio. We move to the next presentation, and we already know Thomas Gruber. Please.
Yeah, thank you again. This time I will not talk about circles or boxes. I will talk about something real. You see this picture? So it's about high-resolution gravity field models in a general sense. You see this a little bit sad-looking picture. This is November in Germany weather, but maybe also November in Rio weather. So, but we will see what happens. I have to change the slide. Okay, so this is work which has been done partially by me, but also a lot by members of our group. So you see some names here. What I would like to talk is a bit about how good are high-resolution gravity models nowadays. Maybe just use it for your reference surface for heights. Why not? As Laura mentioned, to some extent you get reasonable results, and you will see I tried to make an attempt, or I tried to give you a number how good it is. And for this I use usually this GNS leveling as a comparison tool in order to either to test the leveling data or to test the global models. It's sometimes a bit difficult to identify at the end, but usually it depends on the quality of the data and the leveling specifically. Okay, let's have a quick look on the models which I will use here. I started with the very well-known EGM 2008. As you know, this model already contains GRACE data, but no GOES data, or GOJ, whatever you want to like. With Eigen 64 from GFZ, then this already contains GOJ data, in principle the full set of data, but also is based partially on EGM information over land. This is a model we did, which specifically is focusing on the oceans, but which is based on this XGM 2016 model, which contains a 15 minutes global gravity anomalies data set, which we have access. I'll show you in a minute the map for that. There is the PGM 2017 model, which is a predecessor of the future EGM 2020 model. In principle, this is a test model. It's not publicly available from NGA. And actually, a few weeks ago, we computed this model. And now you see even higher resolutions here. So for 5,540 in terms of spherical harmonics. And this is a real large number of parameters, so 2 million or something like that. This is not easy to compute. And you need also the data. For the data here, we use the very dense DTU altimetry gravity anomalies. We use over land only 15 minutes data, but the rest is filled with topography information, so converted topography to gravity. This is not the ideal situation for sure, but it's the idea was to make a completely independent model with data which is available and not use any a priori high resolution gravity information. So that was the reason to make this model. This model is published at the ICGM. Okay, so you should remember a little bit what is done here. So this is the map I mentioned. Actually, it's the same map which was used in the XGM 216 model. This is the availability of data for 15 minutes over land and oceans. And you see in this map, which was more or less given us by NGA, that where is it now? These light gray or whatever it is, fill in, it's called here. These are areas where there's no data in principle. But for all the other areas, there is data included. Good or bad, you never know, in principle. What we do then, from this data set, we estimate a full normal equation system for 700 degree in order 719, 250,000 parameters. And we do individual weighting. So for that, we try to identify the quality of these gravity anomalies, if you want, by some techniques comparing them to satellite information. And then we get a map like this, which shows, in principle, the weights or the quality, if you want, as we estimated from the comparison with the satellite data. You see problems here in that area, sometimes good, sometimes a bit worse data. So, but that drives the whole story. How much impact a specific grid block mean grid value has to the whole solution. For the remaining part above degree in order 719, we use block diagonal techniques, and we use the full resolution over the oceans, 1 minute or 2 minute resolution. And then we add, in addition, as I said, over land, the impact of the topography. So this is the whole model, and that is how it shows now. This is the signal in principle. This is the error. You see the jump here. This is exactly the breakpoint between the full and the block diagonal normal equations, which is difficult to model. Therefore, we have it. Maybe we could do it a bit better in future, but at least it works. And this is the errors here, which errors and differences. It shows a little bit that the estimated errors are at least on some reasonable level. Okay, so you know now about this model. The other models are, I would say, conventional models. What we do here is a comparison of the signal, meaning we make the difference between the old EGM 2008 and these newer models. And this shows you a little bit how much impact EGM has on the other model. So the lower you are, the more you rely on your EGM information. So this just shows you that, for example, the Eigen 64 from 360 roughly relies more or less completely on EGM. Yeah? Therefore, it's below here. Our previous model was here to 720. Independent from that, it relies also on EGM information. These are the two independent models, the PGM and the model which I just explained before, as we call it XGM 2019. You see here the differences are higher to EGM, which doesn't mean it's bad. Yeah? It's just a difference. And you see also our model is even higher in terms of differences. The jump is caused by the missing information above or below 15 minutes spatial resolution over land, where we model it by topography. So this could be good or bad. So it's just a difference, and you don't know. This on the right, you see just a zoom in of the lower part here, which shows basically the impact of the satellite information, which is very similar up to this degree. For the Eigens model, it's a bit lower here. So there is entering EGM information too early in my view. But okay, it's still a good model nevertheless. But so this is very similar here. So this is all driven by the new satellite data. How to quantify what is the contribution of satellite and new surface data frame, maybe. What I show here is nothing else as the accumulation of the previous plot. So in some summary, so the sum of everything. You see the differences of this EGM cumulative is hardly visible up to degree 60, meaning this is driven by grays, and if you add more grays data, it doesn't matter for the static field. It doesn't make any difference. So it will remain here. But then with the models we come up here. This is the area where GGOS enters, from 60 to 200, and you see that all the models which contain GGOS have a larger difference in this part here. And then we have a remaining part here above 200, which is a bit higher than the red one, for example, which is then due to better or new, no, maybe better, but new surface gravity data. So in other words, one can calculate the impact like that. More or less 80% of the total impact is from the new satellite information. So that gives you a real good information. And only 20% is maybe from updated gravity data. So you have to use, also when you do regional geoid computations, you have to use global models which are based on the full satellite information, including the full GGOS data specifically. Okay, I'll leave that. So what I do then is this, I call it here error assessment by GNSS leveling. And this is the computation procedure. I don't want to go into all details, just to mention it. There's a lot of computational stuff in the background. So I compute height anomalies at the GPS leveling station, that means on top of the surface of the Earth. I estimate the omitted signal, which I get from my model, from a high resolution model if available. In this case, I used the old Eigen 64 model because I wanted to be independent from the new data. Above this degree, I estimate the impact of the topography by using this model from Christian Hirt, which models the gravity the impact of the topography also on terms of geoid heights above degree in order 260. This is also available, by the way. And then sometimes I have geoid undulations, sometimes I have height anomalies, and I need to convert. Depends on the comparison data set. So then I apply this in principle old procedure from Dick Rapp, which is also under discussion, maybe. So as Laura also mentioned, this is a weak point in some sense. And then I compare this with the GPS leveling derived geoid information and simply make differences. And the picture shows here the difference. So the red one is the model, this is the real geoid, this is the omission error, basically the difference, and then I make the difference, and that is my quality indicator. When I do that, you will see in a minute, you get also systematic differences usually, which I try to correct by a planar fit to these differences. There are people doing more complicated surfaces, but I'm afraid doing that, to be honest, because you have to have some reasoning behind that, why to do this. So I prefer to stay with the planar fit. And then I just click on these differences. So these are the data which I'm using. Actually, I would like to appreciate Roberto's data which he pointed me on. He showed me how to access the data when I was in IGG in Montreal. So from this very nice tool, by the way, which you have running here at IBGE, so I was able to really use it, even if it was in Portuguese, but I could manage to get all the data loaded from that. And all the other data here, I don't go in each one. For those who have GPS leveling data and not on the list here, I'm happy to receive your data here. So I would really be happy to have some more data also from this area here. Omission error. This is the theoretical omission error, which can also be computed according to the old rule of thumb from Kaula or Channing-Rupp from the degree variance models. And I just made a marker here. At degree 200, the average omission error from these models is roughly 30 centimeters. This is basically in accordance with what Laura also showed. So, but it's the average. You have to be careful. Average means the global average. It could be much more, it could be nothing. So it depends a little bit on the topography at the end. But if you have a model up to degree 2160, it's about 3 centimeters, which is not very much. Nevertheless, again, it depends also a lot on the topography. But it gives you some feelings about how far you have to go with your global model in order to reduce the omission part of the signal as much as you want at the end. This shows the omission error just as an example for Germany, and this is for the Colorado data set. You see here a few centimeters, maybe sometimes a bit more towards the Alps here in Germany, but in Colorado you have much more, 10 to 20 centimeters. This is just an example for converting geoid height anomalies to geoid undulations if needed. This is in Japan. You end up here with more than 10 centimeters sometimes. This is again for Colorado, where you can also get 1 to 2 meters in geoid conversion, which is a critical point to be honest, and which causes probably some of your differences which you have shown, not your, but from the model differences. And then you do the whole computation. These are, for example, for Germany, these raw differences up to the resolution of 2190 in this case for this model. And you see these differences. If you look carefully, you see some tilt, and this is the estimated tilt here, or the surface. And then I subtract it, and then I get these residuals, and you see here 5 plus minus 5 centimeters then at the end. And I can do that for US. This is very well known. I can do that for Brazil, for the new data set, for example, or for the data set which I downloaded. This is the complete data set here. And when you do that, you see here really outliers in that area. And then I estimate this surface, which is looking like this. The residuals are looking like this, and these are still contain systematic effects. So it's not a good way to do it. What I decided then, I excluded these 4 states here. And there's still this blue point, which I don't like, by the way. And then I estimated, and you see the surface is now looking completely different. And these are the residuals. You have here higher residuals. There's still some systematics around here. Maybe you know it probably better. It's just observations from my side. But you see, these are the differences now at the level of 30 centimeters. But the green part is more or less within 10 centimeters, which is not too bad, I would say. So with this high resolution model and this approach, you can get in many areas 10 centimeters. And I claim that these larger differences are not from my model, because why should it be from my model? The model is a global approach. It can only be from leveling, probably. And these are the numbers for these comparisons for all the other states. And the color code says the green is maybe the best one, the yellow middle, and the red one is the worst one. But what you see here is, okay, we don't need to discuss. I'll show you a few more things. This is showing then the for different resolutions. In principle, the RMS average for over each region for different resolutions here, and just a plot. And what you see here is, this is for Germany. You see a level of 1.5 centimeter. So this is a very high precise German leveling and data set, which GPS data set, which is used here. So we can approach we can really get 1.5 centimeters. And if I use these models, you see some differences, but you see the range is altogether here 1 centimeter. It's not very much. You see also the slope here, which is going up here for our new model. This is exactly the reason behind is not having data with higher resolution than 15 minutes, but using topography. And but the impact of this problem or wrong data or wrong approach, because no data is there, is 0.5 centimeter, because or a centimeter if you want, which is still good. The right is US, it's the same. Japan on the left is the same behavior, and this is the Brazilian data set here. You see, in Brazil, the new models have a huge impact. This is the comparison to the old EGM model. And this is the comparison to all models which contain GGOS plus something. And they behave very similar. You do hardly see differences, so the whole system is driven mostly by leveling, higher leveling errors probably. But the impact of GGOS in this case, and maybe some data, is 10 centimeters in terms of RMS of GPS leveling differences, which is remarkable. And this was a good selling point actually for the GGOS mission. By this technique, I was able to convince ESA that GGOS fulfilled its requirements. So they were very happy to see that, by the way. And I'm also happy to have this data set, definitely. It's the only data set where you see the extreme impact. This is for the ocean, so I skipped that in order to save time. So we have this new model up to very high resolution. In global average, I would say the GGOS data improve up to 80% or are causing 80% improvement, 20% maybe from improved better data. It's difficult to distinguish between errors which are from leveling, GNSS, global models, and the different corrections. So you have altogether maybe 4 error sources which contribute to the differences. And now you have to try to separate these error sources. But if I have a sum of 1.5 or 2.5 centimeters, it cannot be too much accumulation from the different errors. Yeah? if you then we have a degradation up above degree 719 because of this data stuff, but it's at a level of a few centimeters. And what would I now conclude about that? What about high resolution model as height reference surface? So depending on the roughness of the surface topography, I would say global models deliver an equipotential surface as geoid high reference at a level of 1 to 10 centimeters. I think I'm a bit more optimistic than you, Laura. At this point, after we did this model, to be honest, so before I would also have said maybe 20 centimeters, but if you don't go to very high topography or very complicated areas, then I would say within 10 centimeters you can make it. So in areas where maybe the gravity infrastructure is not such good, why not use just this such a model, I would say. So, and this is just acknowledgement. So the model is submitted the paper to Journal of Geodesy. This description of how I do all this assessment in principle is an accepted publication for Journal of Geodetic Science. I just don't know what they do since a few months by not publishing it. I would really acknowledge the provision of the different data sets because that is the basis of doing all that work. And then to come back to this picture, at some point the sun will come and then you get a better view of the gravity field again. Yeah, I would like to add two things maybe, which I don't go in detail. I have done this test for all Brazilian states here. By this method I was able now to learn about where is which state at the end. And I did all these differences and I did maps like this and charts like this, which is the same as you have seen before for all states. I'm happy to share that with you. Actually, I will give the data file to Roberto, or you can download it from this computer if you want. So I did all these things. They behave very similar, but maybe for one or the other, you might be interested to have a closer look. I'm just observing, yeah, I'm not knowing about the data. That's a nice thing. And if you allow me a very final statement, I'm sorry. I've put these folders out yesterday, and I had already several talks with some people. This is about a master course we offer in Technical University of Munich, which is about Earth-oriented space science and technology, covering all these features what are discussed here, even satellites, but also techniques to observe satellites and everything. We would be happy to get more applications from South America, and I would like to promote that a little bit for students who are interested in this kind of things. And if you're interested or want to have questions, please get in touch with me. Thank you. Sorry to be long. Thank you.
Thank you very much, Thomas. A quick question, very quick. Thank you. Thank you again. We move to the next presentation. Gabriel, please. 30 years of absolute gravity measurements, South America. Gabriel is professor in Federal University of Uberlândia. Thank you.
Thank you, Roberto. As Silvio said, we are in live broadcast. There are so many students watching. So for this reason, I'll give my talk in Portuguese, okay? Sorry. Bom, boa tarde. A motivação desse trabalho partiu ano passado de um outro trabalho que nós fizemos com os colegas, que foi sobre a evolução da infraestrutura gravimétrica no país. E aí nós decidimos realizar um trabalho sobre os 30 anos da RENEGA, que é a Rede Nacional de Estação Gravimétrica Absoluta, e então decidimos expandir para a América do Sul. Bom, o escopo do trabalho, eu vou, para quem não é familiarizado a questão dos aspectos físicos da geodésia, eu coloquei uma linha do tempo do século passado até hoje, para sintetizar aí os principais eventos, acontecimentos. Depois nós vamos passar aí desde as medidas realizadas na década de 80, 90, nos anos 2000 e hoje, e alguns próximos passos e observações. Eu vejo nessa apresentação 3 objetivos. O primeiro é celebrar os 30 anos de medidas absolutas na América do Sul, homenagear as pessoas que fizeram e ainda fazem pela gravimetria no continente, e também tentar traçar um paralelo aí com a questão do IHRF. Bom, começo aí com o desenvolvimento em 1934 por Lacoste e Homberg, que na minha opinião foi um marco aí para a questão da gravimetria, passando em 48 aí para a apresentação aí para o público do gravímetro Worden. Na década de 50 nós tivemos aí o lançamento do Sputnik, e enfim, em 58 o primeiro gravímetro Lacoste e Homberg é disponibilizado para o público. Essa foto eu tirei há 2 anos, na cidade de Giddings, onde um dos remanescentes da Lacoste, Dan Polk, tem um local que faz manutenção dos gravímetros. Ele me contou à época que o gravímetro ainda funciona, está numa universidade nos Estados Unidos. E aqui uma foto da parte interna do Lacoste. Dificilmente a gente vai abrir um Lacoste para ver o que tem dentro, né? Então, trouxe a foto. Bom, em 76 o lançamento do Lagels. Em 81 o primeiro gravímetro absoluto, o GILAG. Entre 88 e 91 foi onde começou a história da gravimetria absoluta na América do Sul. Eu vou falar daqui a pouco sobre esse programa. 89 o CG3 foi apresentado ao público. 91 ZLS, que é o DORIS, Zero Length Spring, o gravímetro, né? Também foi inicializado. Em 95 teve o lançamento do FG5. No início deste século nós tivemos aí a apresentação do A10 e também o início das missões espaciais com o lançamento do Champ, depois em 2002 com o Grace, e aí apresentado ao público o CG5, 2009 o GOAT, 2016 o CG5 agora é CG6, né, uma atualização, e o ano passado aí o lançamento do Grace Follow-on. Bom, falando das medidas aí que iniciaram na América do Sul na década de 80, 90, graças ao programa de IFE Absolute Graph Program, entre a Universidade de Hanover, o DFG, e também com o apoio do Instituto Pan-Americano de Geografia e História. Na ocasião, estas instituições participaram. Detalhes sobre todo o projeto está nessa publicação. E aqui eu tenho que fazer menção ao curso de pós-graduação em Ciências Geodésicas da Universidade Federal do Paraná, Curitiba, na figura do professor Camille Gemael, que foi um expoente, não somente para nós brasileiros, mas mundialmente. Então, deixo aqui a homenagem ao professor Camille Gemael, tanto que colaborou em termos de geodésia física. Bom, a figura do lado direito traz as estações medidas. Foram 6 estações na Argentina, 7 no Brasil, 6 na Venezuela e 3 no Uruguai, das quais Brasília, Tandil e Santa Helena fizeram parte do que nós chamamos aqui de uma rede internacional. Essa figura também é bastante peculiar, porque mostra a passagem dos equipamentos do Brasil para o pessoal do Uruguai. Se não me engano, aqui na divisa, Rivera e Santana do Livramento, se não me engano. Então ficou registrado aí esse momento. Bom, na década de 90 nós tivemos aí medições conduzidas na Colômbia pelo então DMA e pelo Instituto Geográfico daquele país. Foi utilizado o gravímetro FG5 e foram medidas 3 estações. Já nos anos 2000 nós tivemos aí medições conduzidas na Argentina pelo Instituto francês, o IRD, usando já um gravímetro A10. Foram medidas 2 estações naquela época. A figura ilustra não só as 2 estações, mas também as medidas anteriormente na década de 80, 90. Em 2008, o BGFI recalculou os valores medidos naquela época, entre 81 e 91. Bom, ainda no início dos anos 2000, nós tivemos estações estabelecidas no Chile, pelo BGFI, que já foi mencionado anteriormente por vocês, aí por algum de vocês. 16 estações usando um gravímetro FG5. E no Brasil, em 2006 a 2008, o Observatório Nacional, ontem a Sônia colocou, né, responsável aí pela Rede Gravimétrica Fundamental Brasileira, conduziu 20 estações utilizando um gravímetro A10, a maioria dos pontos aqui na região litorânea. Destaque para a linha de calibração, chamada por nós aí de Itatiaia, Pico das Agulhas Negras, que inicia na cidade do Rio de Janeiro, onde nós estamos, e vai até o Itatiaia. Nós não temos uma variação grande em termos de latitude, mas em termos de altitude, sim, para nós no Brasil é uma variação considerável, cerca de 2.500 metros. Então fica o destaque aí para o Observatório Nacional, que contribuiu aí com as primeiras medições, com uma densificação, vamos falar assim, de estações absolutas no nosso país. Ainda em 2010, no Peru, nós tivemos algumas medidas realizadas também pelo IRD, utilizando o FG5. Foram medidas 5 estações, e o BGI, na Guiana Francesa, conduziu uma estação também em 2010. E na Bolívia, a Universidade de Ohio, Ohio State University, realizou 12 medições, sendo que 3 reocupações. Estas reocupações foram estabelecidas pelo então NIMA, em 97, usando um FG5, porém, em 2010, foi utilizado um gravímetro A10, o 019, 12 estações na Bolívia. Bom, nos últimos 10 anos houve aí uma intensificação no trabalho de estabelecimento de estações absolutas. Muito se deve aí a uma parceria entre o Instituto Geográfico e Cartográfico de São Paulo, que adquiriu um gravímetro A10, a Escola Politécnica e o Senegel, na figura aí do professor Denizar, coautor do trabalho. Então agora eu vou apresentar alguns trabalhos que, pessoal, nós temos realizado aí durante estes 10 anos. Bom, antes disso eu não posso me esquecer de agradecer a todos esses institutos que se envolvem nessas medições. Argentina, Brasil, Costa Rica, Equador, França, virando a página Uruguai e Venezuela. Então, muito obrigado a todos vocês que de alguma forma cooperaram e cooperam para que isso seja possível, para estabelecer essa rede de medições absolutas na América do Sul, em especial também o IBGE, que sempre tem trabalhado em parceria e ajudado nestes trabalhos. Bom, o gravímetro é um A10, não vou entrar em detalhes sobre como é realizado, como é conduzido as medições, por conta do tempo. Nós começamos aí um trabalho na Argentina, que perdurou cerca de 3 anos. Tive a oportunidade de fazer a campanha Sul, saindo aqui de Foz do Iguaçu até Rio Galegos. Foram medidas aí, foram observadas 35 estações. O pessoal do IGN, após o ajustamento da rede, chegou aqui a uma precisão aí de 0.02 miligal para essa rede. Há 2 anos foram estabelecidas 13 estações na Venezuela, sendo 4 reocupações. Foi conduzido aí em parceria com o Instituto Geográfico da Venezuela, Simão Bolívar. No Equador, também em 2016, 25 estações foram estabelecidas. Um detalhe aqui que eu destaco, tanto para a Venezuela quanto para o Equador, é a impossibilidade de medições na região amazônica. Este ano foram estabelecidas 16 estações na Venezuela, embora não esteja na América do Sul, mas acredito que seja importante destacar esse trabalho que foi realizado em parceria com a Universidade da Costa Rica, 16 estações, sendo que 5 foram reobservações, as que estão em amarela. Bom, no Uruguai, durante esse período de 10 anos, nós reocupamos as 2 estações que ali foram medidas no passado, Rivera e Payssandu. E no Brasil, hoje nós temos, além daquelas já medidas pelo Observatório Nacional, nós temos 16 estações que foram conduzidas em um momento e outro, por exemplo, na ida para a Venezuela. Algumas estações foram medidas aqui no caminho. Então, nós temos medições desde Manaus até Santana do Livramento. Ainda nesse período dos últimos 10 anos, nós reobservamos as estações do que nós chamamos de RENEGA, que é a Rede Nacional de Estações Gravimétricas Absolutas, da qual alguns de vocês aí já enviaram gravímetros, seja Lacoste, Homber ou CG5, para fazer a calibração. Então, ela parte aqui de Brasília e vai até Santa Maria. Esse trabalho também nós reocupamos outras estações que não fazem parte da RENEGA, mas que de uma forma e outra aí, colaboram, né, como Cananéia. Estabelecemos uma estação em Monte Carmelo, onde eu vivo, em Lages também. E, bom, fizemos algumas comparações com valores já observados no passado. Bom, algumas fotos aí para registrar o momento. Aqui é em Valinhos, se não me engano, aqui em Curitiba. Ainda no estado de São Paulo, foi conduzido um trabalho com 19 estações, 15 novas e 4 reocupações, Ubatuba, Cananéia no litoral, São Paulo e Valinhos. De 2013 a 2016. Atualmente, se o gravímetro colaborar, né, porque volta e meia ele vai para os Estados Unidos para manutenção, nós vamos fechar aqui uma rede no estado de Minas Gerais. Alguns pontos já foram medidos, porém faltam aí algumas dezenas de pontos. E aqui eu trago, não vou detalhar também, tem outras apresentações, tem trabalhos aí que nós apresentamos as comparações das medidas realizadas em algum momento no passado com hoje, Brasil, Equador, Venezuela, as 4 reocupações, o Uruguai, as 2 estações que ali estão presentes, e a Argentina, que tem uma quantidade maior aí de reocupações. Bom, os próximos passos, está previsto o estabelecimento de uma rede no estado do Paraná, juntamente com o Instituto de Terras, Cartografia e Geologia daquele estado. Estão planejados aí 20 estações e também uma rede no Paraguai. 16 estações em parceria aí com o de Sergimil. Além disso, como já colocado, essa figura já foi colocada várias vezes por vocês. Não é a última versão, eu vi na apresentação do professor Silvio aí algumas atualizações, mas também conduzir medições absolutas nas estações do IHRF. Bom, essa figura traz um resumo do que eu apresentei. Em vermelho aí nós temos as medições que nós conduzimos e que foram conduzidos aí desde a década de 80. Em azul são as estações IHRF. Parte dessas informações eu retirei no BGI, que já foi apresentado pelo Thomas. Saliento a importância de disponibilizar os dados naquele serviço. Saliento também a importância de nós continuarmos com esse trabalho. Na segunda-feira, o Herman já falou da Resolução 3 e da Resolução 4. A primeira diz respeito ao IGRF e a segunda diz respeito ao IHRF. Resoluções decididas em julho em Montreal, no último evento da UGG-IAG. E também trabalhos relacionados à análise dos dados, consideração dos instrumentos, verificação das incertezas, softwares de processamentos têm sido conduzidos aí pela pela equipe, sempre buscando aí a melhoria na qualidade da informação. Bom, é isso que eu tinha para falar. Muito obrigado. Thanks.
Thank you very much for obeying the time. Yes, thank you. Questions, a quick question, Laura, María Virginia. Ustedes tienen que escolher una de los dos. No, por favor.
How is the precision of these gravity values?
It depends on the network. For example, the Argentina network, we have 0.02 milligauss. In Brazil, there is a student work on it. So I can say the whole precision of the entire network because we are working on it.
Maybe for the next version of the presentation, it would be very useful to have a map showing the accuracy of the values.
Okay.
Thank you.
The Ecuadorian measures were before or after the earthquake?
In Ecuador?
In Ecuador.
A ver. Em 2016, professor Denizar, se lembra da data no Equador? ¿Ha escuchado? En el primer semestre de 2016. Bueno.
Thank you again, Gabriel. We must move.
Okay.
Only 10 words, please. Denizar.
Pequeno comentário só da precisão. O gravímetro A10 ele tem uma precisão da ordem nominal de 10 microgal. Nós temos conseguido precisões que ficam um pouco acima, e um destaque importante é para a rede da Costa Rica, onde nós ficamos com precisão de 12 microgal. Da Argentina variou bastante, e no Brasil temos ficado também com alguma coisa um pouquinho acima de 10 microgal, mas muito boa. Agora, a Argentina foi uma rede grande, estabelecida em períodos distintos, chegamos até 17 microgal. Agora, tem uma questão pequena que é o gradiente, que isso demoraria para eu comentar aqui.
Sorry for we have a restriction because of the translation. We must stop at 6 p.m. We move to the last presentation. Dr. Ana Cristina from Nothnagel, a close cooperator of Professor Denizar Blitzko, please.
Good afternoon. I will speak in Portuguese, but the slides are in English. It's very interesting. Laser e mudar aqui. Vou estar falando sobre os geoides na América do Sul, e é muito interessante. Está sendo a última palestra, né? Depois de tudo que se falou até agora, eu vou falar do dia de hoje para trás. E a sessão toda foi daqui, né, do que está para a futura, né? Então é muito interessante, está sendo a última. A professora Passino não pôde vir, mas eu sou aqui a última aqui, né, que sou uma das autoras, e ao final o professor Denizar pode dar mais detalhes. Bom, aqui nós vamos estar falando sobre os principais geoides que estão disponíveis no International Service for Geoid. Esse site é muito importante porque ele tem a história dos modelos geoidais no mundo todo. Seria muito interessante que as pessoas disponibilizassem os seus geoides, modelos geoidais e quase geoides, nesse site, né? E aqui nós vamos estar falando na primeira parte sobre os que estão disponibilizados nesse serviço. Aqui mostra uma figura e vamos lá. Então vamos começar por ordem alfabética, começando pela Argentina. O primeiro geoide original oficial foi em 1998 e esse é o único geoide que não está disponível no serviço. Os outros 3 estão. E o 2016 é o oficial hoje do Instituto Geográfico Nacional. E aqui eu dou em destaque, né, a publicação desse modelo geoidal e foi com relação ao cálculo, foi da tese do Pinhon, doutorado do Pinhon, que hoje tem esse modelo geoidal, a Argentina. E aqui eu dou cada geoide que eu vou estar falando, dá um pequeno resumo. A resolução é de 1 minuto, os dados gravimétricos foram usados dados gravimétricos terrestres, a técnica remover, calcular e restaurar, né? E o modelo geopotencial foi o GOCO 05S até grau e ordem 280. A integração foi usada, a integração da integral de Stokes modificada foi usada o FFT com kernel Wang Gore. O modelo digital de terreno foram 2 modelos do CRTM e o modelo de altimetria DTU 13. Nesse modelo houve um ajuste dos pontos GPS sobre nivelamento. E na última linha a gente mostra a consistência, né, desse ajuste usando 1.891 pontos GPS sobre nivelamento. Foram 5 centímetros. Na Argentina, também tem outro modelo geoidal, de 2017, foi calculado na Universidade Nacional de Rosário, em convênio que foi um projeto em conjunto com a Universidade de São Paulo. Ele foi publicado na GeoActa, e aqui é uma das características. Ele tem resolução de 5 minutos, dados gravimétricos terrestres, aí, no caso, o modelo geopotencial foi o DIR-R5, até grau e ordem 300. Aí a integral de Stokes modificada, FFT, com um núcleo diferente, Molodensky-Massel. O modelo digital de terreno foi o SAN 3 segundos V2, que ele é baseado também no CRTM, de 3 segundos, somente que foi removido a altura geoidal do EGM96 e foi acrescentado do Ågren GL04C. Não teve ajuste dos pontos GPS sobre nivelamento e a sua consistência foi usada 100 pontos com GPS sobre nivelamento e foi de 22 centímetros. A Bolívia também tem um modelo geoidal no serviço de IGS. E aqui as características dele foi de 2006, 1.5 minutos, dados terrestres, remove compute restore. Aqui mostra o modelo geopotencial, até grau e ordem que ele foi usado. Aí ele informa que também usou a técnica FFT para integrar. Usou o CRTM de 3 segundos, não usou modelo de altimetria, não teve ajuste e a convergência do modelo geoidal com relação a 17 pontos GPS sobre nivelamento foi de 45 centímetros. Aqui no Brasil, houve 4 modelos geoidais oficiais pelo IBGE, sendo que esse, em 1992, não está disponível no serviço, mas os outros 3 estão. E o último é o MapGeo 2015, que aqui está em destaque a publicação. Também tem a apresentação dos SIRGAS também, desse modelo geoidal. Aqui vale destacar que, para o cálculo do MapGeo 2010, antes disso, houve um convênio, um projeto do IBGE com a Universidade de New Brunswick. E o professor Vanisek e o Arthur Hellman vieram para o IBGE para ensinar a calcular o pacote computacional da universidade, o SAGO. E o MapGeo 2010 e o MapGeo 2015 usam parte desse pacote computacional. E ele tem uma resolução de 5 minutos, dados terrestres, remove compute restore again, o modelo geopotencial usado, o Ågren CC4, até grau e ordem 200, a integral também modificada de Stokes, o FFT, e aí, no caso, o kernel foi o Molodensky-Messel. O uso do modelo digital são 3 segundos, altimetria, modelo de altimetria DTU10 não foi ajustado, e a convergência de 592 pontos com o modelo geoidal foi de 17 centímetros. Agora, em 2014, a tese do Gabriel foi porque essa região de São Paulo é muito interessante. Ela tem vários projetos, ela tem uma densificação muito boa. E, no caso, foi justamente para testar duas formas de integração. E aí ele fez esse cálculo, e na hora, aqui, que vocês podem ver, ele tem 2 modelos disponibilizados. Um com FFT, outro, a integral de Stokes, não modificado, foi calculado para FT, e outra por colocação de mínimos quadrados. E aqui nessa região, usou 363 pontos GPS no nivelamento para estudar a convergência do modelo geoidal com esses pontos. Deu 20 centímetros. A Colômbia então, tem 2 modelos, um quase geoide e um geoide, que é de 2004. Aqui está a publicação da Laura, né? Aqui. E a resolução de 2 minutos, tem dados terrestres e aéreos. Usa o modelo TEG-4, até grau e ordem 200. Técnica FFT, modelo digital terreno de topo 30. Altimetria de radar, o modelo foi o Sand-Smith, versão 9.1. Aí, na hora analisar com relação aos pontos GPS, ela tinha uma linha de nivelamento de 300 km, que tinha 38 pontos, e deu uma convergência de 55 centímetros, e pontos distribuídos pela Colômbia, 25 pontos, deu uma convergência de 71 centímetros. O Uruguai tem 2 modelos, 2000 e 2007. Esse é a última publicação do último, oficial do Serviço Geográfico Militar. Ele é de 2 minutos, dados terrestres, usa outro modelo geopotencial, GGM02C, técnica FFT para resolução da integral, CRTM. O modelo de altimetria KMS02 não foi ajustado. E aí, para ver a convergência com os pontos GPS no nivelamento, ele usou 50 pontos e deu um valor de 2 centímetros. Aqui tem os modelos geoidais. Tem 2 modelos geoidais disponibilizados no serviço, de 2010 e 2015. Geoide 2010 e geoide 2015. Aqui está a publicação. Também tem no SIRGAS a apresentação sobre ele. Ele é claro, já que 5 minutos, está acabado. A colaboração de várias instituições. Ele tem essas características, eu vou já então 5 minutos, dados terrestres aéreos, GOS, Ågren CC4, 200, e aqui no final, eles usaram foi testado com 1.319 pontos, deu 46 centímetros de convergência, e aqui mostra separado para cada país. Esses 1.319 é a soma desses pontos. Isso aqui no total, e aí a análise separada de cada país. Tenho esses 2 últimos aqui que eu vou apresentar, não estão no serviço, International Service for Geoid, mas a Venezuela tem 2, 2004 e 2015, mas ele está disponível, esse em especial, o último, está disponibilizado nesse site. Ele é de 3 segundos, aqui mostra o modelo geopotencial, integração por FFT, modelo digital terreno usou CRTM, o modelo de altimetria DTU10, ele foi ajustado e tem uma consistência de 12 centímetros. E o último é do Chile, norte do Chile, que é foi apresentado no Congresso de 2018, é o mais recente, e ele tem aqui essa resolução, e não, como podem perceber, ele não foi ajustado, e aqui não tem uma consistência, porque, na realidade, a rede de nivelamento do Chile foi destruída com os terremotos, então não teria como, ainda não foi recuperado, então aí não teria como eles estarem fazendo um estudo, uma análise. A diferença, só que eles compararam com o EGM 2008, e eles falaram que a diferença maior estava justamente na fronteira com a Argentina. Aqui mostra um resumo deles, todos, né, com as suas consistências, aqui embaixo. Tá certo? Todos eles usaram diferentes modelos geopotenciais, mas, no geral, aqui está o CRTM, de formas diferentes, em resoluções diferentes. A maioria usou FFT. E o que vale destacar aqui, os pacotes computacionais, tanto a escola do geóide, que já teve 3, né? Então, quando você vai ver as publicações, muitos usaram esses programas computacionais, que permitiu vários países poderem estar calculando seu próprio geóide. Aqui só um resumo da técnica de integração. E é isso. Eu achei muito interessante essa sessão, justamente porque a Laura Sánchez falou justamente no segundo slide sobre o que está 2 grupos, um grupo de estudo, um outro grupo de trabalho, sobre o Colorado, que ela falou bastante sobre ele, e tem um grupo de estudo sobre geóides e quasi-geóides regionais, né? Então, existe esse futuro. O Silvio deu uma importância muito grande sobre o datum IHRE, a unificação, né? Que é super importante para nós aqui, calcular o IHRF, o potencial para os pontos IHRF. Então, tem todo um futuro, né? O Thomas sobre os modelos geopotenciais, que foi muito interessante. Então, tem toda uma história aí para frente que todo mundo vai ter que trabalhar.
Thank you very much. A quick question.
Denizar, quer falar alguma coisa?
Um pequeno comentário bem rápido aí, para não prolongar muito, né? É importante enfatizar que os levantamentos gravimétricos que foram realizados desde 1992 nos diferentes países, como Argentina, Chile, Equador, Venezuela também, até recentemente, é que permitiram esses diferentes modelos geoidais aí na América do Sul. Alguns países, como vocês viram, realizaram esforços particulares, como a Argentina, e outros países ainda estão aí fazendo algum esforço. E eu queria deixar uma observação importante, que nesses levantamentos todos aí nos diferentes países teve uma grande contribuição do IBGE. Quase sempre o IBGE participou aí dos levantamentos e, em muitos casos, ofereceu o treinamento necessário para o pessoal dos diferentes países.
Thank you, Denizar. Laura?
Qual que é?
No.
Vai falar depois?
Not for you. Any? Okay. We close here. Laura has some question.
Just a little question. Usually in the SIRGAS Symposium we publish the presentations at the web page, and for the GGOS days we publish the presentations at the GGOS web page. So the speakers from today agree to publish the presentations in these 2 pages, or if someone doesn't agree, could you please let us know that we shouldn't publish your presentation at the pages? Yes? So we assume you agree to publish the presentations at our web pages. Yes? Okay.
Thank you again for everybody, for all the speakers, for the audience. Thank you very much. I have only one question for you. Virginia Mäkinen nos pide para que los interesados en participar de la reunión de SIRGAS tiempo real, mañana al almuerzo, que levante las manos, solo los interesados en participar de la reunión, para cuantificarmos la comida. Ustedes van a pagar el doble. Gracias. Thank you very much. See you tomorrow. Have a nice back to hotels and home and so on.